Okay, so this is going to be the review session for MA 213, the final exam. So we are here 2 days before the final. A few notes about the final exam first. So it's going to be a little bit different than the midterms, just in terms of how many questions there are. So it's going to be 3 free response questions, and it's going to be 3 multiple choice questions. Okay. The exam duration is 110 minutes. And then for the in-person group, it is in LSA 191. That's the very big classroom in life sciences. And then for the online students, I believe Dr. Peralta has given you guys your instructions. So just refer to his announcements on that. For the free response questions, I can tell you right now exactly what the topics are going to be. One free response question is going to be an axial problem. One free response question is going to be a torsion problem. And one free response question is going to be a bending problem. And this one right here, I can guarantee you that this one is going to be statically indeterminate, because we have not yet tested statically indeterminate beams and bending, and it's an outcome of the class. So I don't think we've ever had an exam where statically indeterminate beams is not tested on the final. So this one will for sure be statically indeterminate. Between the torsion and axial problems, they do tend to make those statically indeterminate as well, but I'd put it as pretty much a toss-up on either one. I'd say be prepared to solve statically indeterminate problems for these guys, but it's not necessarily going to be statically indeterminate. After that, for the multiple choice questions, that's fair. Anything from the entire class is fair game. So you might have a problem maybe on thermal stresses, thermal strains. You might have a prismatic beam design question, where you're looking at your tables and trying to figure out what shape you need to use. You might have a stress strain curve that you need to look at. So, it really could be anything, because at the end of the day, this is a cumulative final. I think that covers everything as far as the exam format and content itself. Let me see. How many questions are the free response and multiple choice worth? Off the top of my head, I don't know the exact numbers. I suppose I could see if I can pull up a previous final. It might take me a bit too long to do that though. So I'll tell you that generally it's the same weighting as the midterms as far as between the free response and the multiple choice. Okay, so on the midterms, I think it was like 70% or maybe 70 to 80% of your points were free response, and then the rest was multiple choice. So I would say probably a similar distribution here. Actually, I think there's an example final exam that's been posted. Ooh, this was my final exam. Let me see if I remember it. Okay, yeah. So in this final, there was the multiple choice questions were worth 8 points each. Problem 4 was worth 24 points. Problem 5 was worth 24 points. And problem 6 was worth 28 points. So let's see, what is the math on that? So 24 and 24 is 48. 48 plus 28 is 76. So yeah, about 3/4 of the points is from the free response, and then the last quarter is from multiple choice. If they ask for bending and shear diagrams for an axial problem, they're probably not going to ask you to do that for an axial problem, because it doesn't really make sense to do that. They might ask you for the axial load diagram. They might ask you for the axial load diagram for the axial problem, but shear and bending moment diagrams, that'll probably be reserved for the bending problem. I mean, I don't expect that they would ask that twice. And so if they're going to ask you to do shear and bending moment diagrams, it'll be on the bending problem. Obviously, for the bending problem, you would go ahead and do the graphical method. If they did ask you for, like if they have a triangular distributed load or whatever as a multiple choice question, and they ask you to find the bending moment, there, you can use graphical method or method of sections. For a multiple choice question, I'd probably say do method of sections, just because we haven't done too many problems with triangular distributed loads with graphical method. But again, use your best judgment based on what the problem is asking. Any other questions on exam format or content? For online, what tables will they give us access to? Everything, every table that you need. So you're not going to be asked to memorize the superposition tables. You're not going to be asked to memorize the prismatic beam design tables. You'll be given those if you're asked about it on the final. And that goes for the in-person group as well. So you're not bringing any notes with you. Any tables or properties that you would need, those will be given to you. Not moment of inertia, though. Moment of inertia, that's something that you do need to calculate yourself. Okay, so kind of one more note quickly, just at the onset of the review session here. So this review session does tend to be a little bit different from the first two midterms, and here's why. On the final, I don't do conceptual review. The reason being is that I've already done the conceptual review. So what I'm going to say before we begin is, if you would like to review the theory for any one of the concepts throughout the entire course, go ahead and look on Canvas on the announcements for the first two midterm reviews and look at the timestamps, okay? So I put timestamps on the first two midterm reviews, and that includes the parts where I'm just doing theoretical review, okay? So that is where I will direct you for any conceptual review. Obviously, as I'm solving the problems, I'll be talking about the theory behind it, but I'm not going to do a deep dive the way I did in the first two midterms, because otherwise we will be here for 8 hours, and that is just too long even for me. So with that, the way this review is going to shape up is I'm going to do a whole bunch of problems that cover the entire course. So we're going to start with axial, then we'll take a break, we'll do torsion, then we'll take a break, and then we will do bending, and then we'll be done. I will say that we are going to do theoretical review for statically indeterminate beams and bending, because that's the only thing that I had not covered on the first two midterms. But everything else has already been covered, and I want to make sure that we're respectful of everyone's time here. And don't worry, still plenty of content to go over. So with that, is everyone ready to move on to and get started with our first problem here? Any guess how long this will go? Well, every time that I've made a guess, it's been in about an hour longer than I expected. So I'm just going to say it's going to be a few hours. For this one, I am hoping that we'll be done by 2, just because I'm not doing any theoretical review. But at the end of the day, we'll see. Are we going to go over some multiple choice questions in the spring 2019 exam? If there are any that you would like me to go over, just go ahead and post them when we're talking about the corresponding problem, and then we'll review them. I know someone wants to review the number 5 of spring 2019, so that one I will cover. At the end of the day, any additional problems that you guys want to do, we can go ahead and cover those as well. So, all right, let's do this. So the very start of the class, we started with just using method of sections to figure out all of our internal resultant loadings, okay? So what we're going to do here is let's go and solve this problem, and just as a warm-up, never hurts to just draw the free body diagram and solve for support reactions. So I know that I'm going to have a couple moments here on the left side. I'm going to have a support reaction AY. Don't need to worry about AX, because that is well, actually, because we're asked to find N of X, I'll just go and draw AX here. We have a 2 kilopound per foot distributed load here. And then we have a triangular distributed load here, and then a point force here at the very end. Okay, so first things first, we know that sum of the forces in the X tells us that AX is going to be equal to 0. Next, sum of the forces in the Y. We have 2 resultant forces here. So we have the resultant force that's from the rectangle, which is 2 kilopound per feet times the distance over which the load acts. So that's just 6 feet. So we have that this is 2 times 6 equals 12 kilopounds. Then for this right portion, we have the triangular distributed load. So for the resultant force of the triangle, we have 1/2 times the base, which is 3 feet, times the height, which is 2 kilopound per feet. And that gives us a resultant force of 3 kilopounds. So with all that, AY goes up, the 12 from the rectangle goes down, the 3 from the triangle goes down, the 4 at the end goes down. So we have that AY is going to be equal to 19 kilopounds. Okay. Next, sum of the moments about A. So then we're just doing the moment from each one of these. First of all, we have the couple moment MA, which is drawn counterclockwise. We have the couple moment at the very end, which is drawn clockwise. So that shows up as the negative. Then we have to draw our resultant forces to figure out where the moment arms are. So for the rectangular distributed load, we have that it's acting halfway with a clockwise moment. So I'd have minus 12 kilopounds, and then my moment arm is going to be 3 feet. And then just to be consistent with units, we have this. Then for my triangular distributed load, it's going to be 3 kilopounds. And then your rule for triangular distributed loads is that it's a third from the peak. Okay, so a third from the peak tells us that this distance right here is 1 foot. So then my overall moment arm is 7 feet. Oops. And then don't forget, we have one other force to deal with. So we have minus 4 kilopounds, and that one is acting all the way at the end. So we have this. All right, so MA is going to be equal to the sum of all this crap. So we have 20 plus 36 plus 21 plus 36 equals 0. So that's, oops, don't know why I had equals 0 there. Then 72 plus 41, that gives you 113. Someone feel free to check my math on that. I should be right. Okay, so we have all of our support reactions. So let's go ahead and redraw the free body diagram. Okay, so we have 113 kilopound feet here, 19 kilopounds here. Still got both of our distributed loads. And then the triangular distributed load at the end. Make sure you dimension everything. There we go. So to figure out our internal resultant loadings, we know that we need to go ahead and make some cuts. So obviously we have 2 cuts that we need to make because my external loading changes twice, right? Once at the very beginning because we're on the beam, and then once here when we go from a rectangle to a triangular distributed load. Okay, you get to choose which side to keep. In this case, for region 1, I'll say that I keep the left side. So let's see how this works. We have 19 kilopounds here, 113 kilopound feet here. My distributed load of 2 kilopound per feet, that acts over just the remaining portion, which I define as X. And then we get our internal resultant loadings going, remembering, of course, our sign convention, right? That says that normal force always comes out, shear force is drawn positive going down, bending moments drawn counterclockwise when you keep the left side. Then it's another round of equilibrium equations. So we know that N1 is equal to 0. Then I can go ahead and sum the forces in the y direction. And now we have 19 going up and my resultant force going down. For my resultant force, I know this is just going to be the distributed load times this distance x. And then I've drawn V1 going down here. Okay, so we have V1 of x equals 19 minus 2x. Then go ahead and sum the moments. When you're doing method of sections, it's always best to sum it about the cut. That way you don't have to worry about a messy expression for your shear force being thrown in as well. About the cut, we have 2 counterclockwise couple moments. We have M1 of x and then 113 kilopound feet. I have a clockwise moment from 19 kilopounds. So we have minus 19 kilopounds times the moment arm is x. And then finally, I have the moment from my rectangular distributed load, which is the resultant force, right? So the resultant force I found was 2x. And then my moment arm is just the halfway distance. So we have x over 2. All that equals 0. So then we have m1 of x equals 19x minus x squared minus 113, okay? And again, one important thing to note, derivative of the bending moment is equal to the shear force, right? We know that from when we were talking about graphical method. Always useful to check very quickly when you're doing method of sections. Okay? Any questions on getting the internal resultant loadings for this first region here?
So just to confirm, because I kind of forgot from midterm one, we consider another reaction moment at the left-hand side because of the wall support.
Yes. So this is a fixed support, so it blocks rotation. Because it blocks rotation, it has to supply a couple moment.
So anything else like a roller or a pin wouldn't cause any reaction
It would have
moment,
a
right?
reaction, but the reaction would just be a force.
Okay.
Support reactions, supports, you only have the reactions that correspond to what motion they block. So because pins and rollers block motion in the vertical direction, that's why they have support reactions in the y direction.
Okay. Sounds good. Thank you.
No problem. So for this second region over here on the right side, we know that we can either choose the left side or the right side. And I think we kind of have seen by now that it tends to get incredibly messy when we're working with trapezoids. So it's much better here to go ahead and keep the right side. Okay, so redrawing everything as is, we have a portion of the triangular distributed load, and its intensity will denote by W of x, and then 4 kilopounds here. Okay. Next, what we're going to do is we're going to recognize that this distance right here is s, right? Something other than x, because since I define x from the right side, from the left side, excuse me, s is defined from the right side. So then I can write x plus s equals 9 feet. So therefore, s equals 9 minus x. And that's the substitution we're going to make to change everything back to be in terms of x. With this substitution in mind, I'll go ahead and work on just what I have here. So I'll actually go ahead and change this to W of S. All right. Next, what I need to do is I need to make use of similar triangles to figure out what W of S is. So let's go ahead and work with that. We know that over the triangle, I have 3 feet. That's the entire length. And then its peak height is 2 kilopound per feet. And then I have a smaller triangle somewhere in the middle here. And that has a height W of S, and it has a length of S. Then by similar triangles, we know W of S over S equals 2 kilopound per feet over 3 feet. So then we have W of S equals 2 over 3 kilopound per foot squared times S. And don't be thrown off by the units here. These are the correct units I need to have because I know that S is going to be a unit of length, and then a distributed load intensity is always unit of force over unit of length. Okay, so this is fine. Next, now that we found W of S, let's go ahead and run through our statics, okay? Or our equilibrium, I should say. So we have N2 here, V2 here, and M2 here. Obviously, we know that N2 is going to be equal to 0 because there's nothing balancing it out. Then, summing the forces in the y direction, we have V2 of x going up. And then for my resultant force, now that I've found W of S, what I can do is it's just going to be another 1/2 base times height. But here the base is S, and then the height is W of S. Okay. Then I have the 4 kilopounds going down. So that's perfectly fine as is. So we have V2 of x equals 1/2 S times, now make this substitution, times 2 over 3 S. And then plus 4 equals 0. So then simplifying it out, we have just S squared over 3 plus 4. I don't know why I have the reflex of doing equals 0 there. Sorry about that. Okay. So again, all of these internal result loadings, we're just doing equilibrium equations for given regions, okay? The only tricky thing here is working the distributed load, okay? So we have this, and then last but not least, let's go ahead and make our substitution. Is V2 of X. Sorry, right now it's V2 of S, so I need to be careful about this. If you do that on the exam, I wouldn't sweat it too much. Just don't report this as your final answer. If you report it as your final answer, it's wrong. Okay. So what we're going to do is change that to S. Then what we'll say is V2 of X is going to be when I make my substitution. So I'm going to have 9 minus X squared over 3 plus 4. Shouldn't 6 be in the denominator? Where am I? Yeah, so we have a 2 on the top and the bottom. Okay, there we go. So problem solved. Okay, so now once I've made the substitution to X, we're good to go. Let's go ahead and sum the moments about the cut again. So then we have a clockwise couple moment in M2 of S, and then another clockwise moment in 20, and then a third moment from the point force. So we have minus 4 times S. And then finally, to handle the distributed load, I know that my resultant force is this, okay? So put another way, oops. I'm denoting this as the resultant force just so I don't have to write it all out again, okay? Now, this resultant force has a particular moment arm, which we know that even though it varies with S, it still obeys the same rule as a triangular distributed load, okay? So I would select for my moment arm S over 3. So then we have our moment is the resultant force times the moment arm, which is S over 3. Okay, then solving for M2 of S, we have 20 plus 4S plus the resultant force, which is S squared over 3 times S over 3. And I can simplify that one more time. You can get M2 of X equals 20 plus 4S plus S cubed over 9. Finally, we'll make our change of variables to get M2 of X. So we have 20 plus 4 times 9 minus X plus 9 minus X cubed over 9. Okay. Any questions on that?
So do we expect to be asked to find the constants and do the integration method on a free response question, or would it be a multiple choice like the midterm too?
I didn't really hear the question. Say that one more time.
So you know, like how we use integration method to find our constants, and then
That's for
start with the
beans.
method. Yeah, and for the method of section, do we expect that on a free response
Well, this
problem?
is method of section, so this has nothing to do with integration.
Right, but we just use that in order to integrate it twice and find deflection. So,
Oh,
um,
I see what you're saying.
yeah,
Yeah, so if you were asked to do deflection by method of integration, then you would make use of method of sections. Yep.
okay, and
Graphical
like
method does
midterm
not. Yeah.
and like midterm too, do we expect that on a multiple choice problem or a free response as well?
I can't say for sure. I mean, it's been asked on I've seen it on both multiple choice questions and free response questions before. Since they already asked you a deflection question on the midterm, I don't know that they would ask it again as a method of integration question. But it is fair game, is what I'll say.
Okay, sounds good.
Okay. So I think I made a mistake here, guys. So when I take the derivative of the bending moment here, this term checks out, but here I have a sign error. So let me go ahead and quickly see where my mistake was made. Do you have a clockwise moment there? That part's fine. Ah, Yeah, so that means I have that this should be clockwise. So that should be negative. So then what does that change? That means that all of my signs get flipped. Can we leave the m of x and v of x equations like that, or do we have to simplify them? If they ask it, they're probably not going to ask you to simplify. I will say in the future, we're probably going to have a way of, like on homework questions, for example, you can use MATLAB to simplify it into a simple polynomial expression, but here I wouldn't worry about that. So, just leave it, like this is perfectly fine. Okay, so let me see what's going on here, guys, because there's a problem with the signs. So we have all of these terms are clockwise about the cut. So then I need to flip my signs on each of these guys. Okay, then we have, so minus 4s, minus 20, minus 4s, minus s cubed. Well, that takes care of one term, but then the other one's screwed up. So let me look at this a little bit more carefully. No, we're good because when I take yeah, so that's fine. When I take the derivative of this, we get 9 minus x over 3 squared, but then by the chain rule, it becomes positive. Okay, now I think we're good to go. So let's go ahead and summarize our results, and this is how you'd want to report them. So for our two regions, we have 0 to 6 and 6 to 9. Whoops. So we found n1 of x is 0. v1 of x equals 19 minus 2x. And m1 of x is 19x minus x squared minus 113. Then for 6 is less than x is less than 9 feet, we have n2 of x equals 0. v2 of x equals 9 minus x squared over 3 plus 4. Then m2 of x equals negative 20. And we'll actually go ahead and change the sign here. Plus 4 times x minus 9. And then minus 9 minus x cubed over 9. Okay. All right, so there we go. That is our method of sections problem. Again, I don't know to what extent they would ask about this on the final, but since it is our bread and butter of the class, always good to just be comfortable with this. When in doubt, make a cut. See, I'm already having technical problems here. 1 second. How did I fix that before? There was like on the second midterm, there was something that I did that fixed it, but I don't know what it was. What did I change the sign on for? So I didn't technically change the sign. I more or less just distributed the negative so that it's more friendly. I don't like having two negatives here. It's kind of nicer to just distribute the negative and then have a positive here. It's also easier to see that the sign matches up when you take the derivative.
So is this accurate now? The final thing that you've boxed?
Yes. And we know that it should work, right? Because when I take the derivative of the bending moments with respect to x, I get the shear force expressions.
So I guess I'm unclear why the 4 times x 9 minus x. Oh, you just flipped it. You made it x minus 9.
Yeah, so yeah, right? If I, distribute this out, negative 36 plus 4x. So that's 4x minus 36. So that's 4 times x minus 9.
I see. So it would be equally accurate to say minus 4 times 9 minus x.
Yes, but
Yeah.
the only trick is when you take the derivative of that, be very careful with the chain rule, right? Because then you have a lot of negatives being thrown around.
Right. That makes sense. Okay. Thank you.
Any other questions on that? All right, let's do our next problem. So after method of sections, let's do question. Other than deflection, method of integration, are there any problems that would... Okay, so method of sections, you use it in every single problem. The thing is here, we're using it to find loadings as a function of x. Loadings as a function of x, that is a pretty narrow range of questions. But method of sections, one way or another, you use it in like 90% of the problems. The only time that we don't use it explicitly is graphical method and statically indeterminate beams by superposition. But every other problem, like axial loads, we make cuts. Torsion problems, we make cuts. Anything like that, you're using method of sections. No, you don't need to simplify more than that. Okay, so there's not enough time to run this through a polynomial calculator. Just like this, I would expect that it's fine. And especially because, you guys saw in recitations, simplifying can be a little tricky, right? Because you're multiplying a lot of things together, right? The fewer steps that you need to make yourself, the less likely it is you make a mistake. Okay. All right, let's do our next problem. So this one is a mechanical properties of materials problem. So this is one of the other topics we talked about when we're talking about axial loads. So let's have a look at this. The first thing we're going to notice is that we're given a stress strain curve. Okay, so if you see a stress strain curve, you do not have sigma equals E epsilon necessarily. Okay, that only applies in elastic region. Okay, you don't know whether or not you're in the elastic region when you're given this stress strain curve. Okay, so in these problems, you need to first calculate the stress, then calculate the corresponding strain based on the curve, and then from strain calculate elongation. Okay, so be very careful about that. I know there were a few issues with that on the first midterm. So first things first, let's go ahead and get what our stress is. So we know that the stress is, of course, the load over the area. My load is 150 kilonewtons. I'll go ahead and change that to newtons. And then my area, I know it's pi over 4 times the diameter squared. So 400 millimeters squared. And I'm leaving it as newtons per millimeter squared because we know that that's going to be equal to megapascals. Okay. So without needing to do any unit conversions, I can just do 150,000 divided by pi times 100. We get that we have 477.5 megapascals. That's my stress. And then I see that that lands me in this region right here. Okay, so that means that I'm not in the elastic region. I need to find the equation for this line. To find the equation of this line, we talked a little bit about it in the first midterm review, how we can use point slope form to figure out the equation. So what we're going to do is we're going to say, let's apply point slope form to this line. All right, so my expression is going to be sigma as a function of epsilon minus sigma 1 equals my slope, which I'll call E2, times epsilon minus epsilon 1. Now, sigma 1 and epsilon 1, I can just go ahead and make use of either one of these 2 points, right? I'll go ahead and use 500 and 0.03. So we'll say that sigma 1 equals 500 megapascals, and epsilon 1 equals 0.03. Next, to find E2, I can just do rise over run. So my rise is going to be 500 minus 450, and then my run is going to be 0.03 minus 0.00225. And then the top is, of course, megapascals. So calculating this out, we have 50 over 0.03 minus 0.00225. That gives me an E2 of 801.8 megapascals. So then my equation for this second region is going to be sigma as a function of epsilon equals 1801.8 megapascals times epsilon minus 0.03 plus 500 megapascals. Okay, so that is for 0.00225 is less than epsilon, is less than 0.03. Definitely good to be familiar with point slope form because I think it's generally the fastest way of analyzing stress strain curves. Okay, so definitely want to be comfortable with that. Next, what we're going to do is we're going to go ahead and plug in the value for sigma that we found. So we know that sigma equals 477.5. We need to figure out where exactly it gets to on this diagram. Okay, so to do this, we're going to go ahead and substitute. So we'll have 477.5 megapascals, and then that equals all of this. So draw another line so I don't run out of room. Then going through the algebra, you're going to get an expression that looks something like this. So we're going to take the difference of the added terms, divide it by 1801.8, and we see that now we're working just with unitless quantities. So we get this. Question? Might have been just someone clearing their throat. All right. So then let's go ahead and throw this into our calculator and see where that takes us. So we have 477.5 minus 500 over 1801.8. Then add on 0.03 to that. We get a strain of 0.0175. An important thing to check when you're doing this, make sure that if you're in your second region, whatever strain you get really falls in. If I got a strain value of greater than 0.03 or less than 0.00225, I got to go back and check it again, right? Because then that means that I've mucked up the algebra somewhere. But in this case, we know that we get to a point that's right around here. Okay, this is not drawn to scale, but that is my elongation that I get to once I load it. Now, an important point here. Once I let go, we're not just going to go back to zero, right? Because we've passed the yielding point where the slope changes, that means that when I let go, it's instead going to unload along this line right here. And that line has the same slope as the elastic region. Okay, so then the permanent elongation is this part right here, or the permanent strain, I should say. And then this part right here is the recovery strain. All right, so to figure out what epsilon p is, we again just make use of point slope form. So we already know the value of this point, and then to figure out epsilon 1, I know that epsilon 1 is just going to be 450 megapascals over 0.00225. And that's going to give me, I think this is a steel stress strain curve. Yeah, so I get 200,000 megapascals. So I know the slope of this line, I know a point on this line, and I can go ahead and make use of point slope form. So my recovery line, I'm going to write as sigma recuv as a function of epsilon. That minus my stress value of 477.5 megapascals equals 200,000 megapascals times epsilon minus 0.0175. And now that I've got the equation for this line, I can go ahead and plug in sigma equals 0, and sigma equals 0 will let me pick out epsilon p. So let's go ahead and do that. 0 minus 477.5, divide through by 200,000. Both of these are in megapascals, equals epsilon p minus 0.0175. So then solving for epsilon p, we do negative 477.5 over 200,000, and then add on 0.0175. So we get that epsilon p equals 0.0151. Okay, again, checking our results. Obviously, our permanent strain should be less than the overall strain I got when I loaded this thing. Okay, So a permanent strain right here is perfectly reasonable. And then of course, epsilon P plus epsilon R equals 0.0175. So if I wanted to find the elastic recovery, it would be using this formula. Finally, once we have the permanent strain, we know that the elongation, right? Epsilon is just delta. Strain is elongation over original length. We're told that this specimen has a length of 50 millimeters. So then delta equals 50 millimeters times 0.0151. So that gives me a permanent elongation of 0.756 millimeters. So specimen permanently elongates by 0.756 millimeters. Okay, so when you're working with stress strain curves, the important line of attack that you want to be comfortable with is point slope form. That saves you the most time. When you have a stress strain curve, make sure that you calculate stress and strain separately. Okay, so calculate stress first, then figure out what the corresponding strain is using your stress strain curve and go from there. Will we lose points for a question like that if we use a different method but get the correct answers? No, you will not lose points. Okay, so they're just asking you, they're not, if they don't specify a method to do it, you can use whatever method you'd want. I suggest using point slope form because it saves you the most time, but you don't have to use point slope form. If you want to use similar triangles, go for it. Can Hooke's law be applied if we pass the plastic area? No. Hooke's law is only for the elastic region, okay? Even though this second region here is linear, you don't want to call it Hooke's law. It would be a mistake to call it Hooke's law, right? Hooke's law is this very specific relationship right here where it's not just linear, it's proportional, okay? Outside of the elastic region, you are not proportional. You're linear potentially, but you're not proportional, okay? So you don't want to just use sigma equals the epsilon. You want to use some of the tricks here. And then point slope form is just interpolation. Yeah, I mean, I guess here I did split it up into a few steps here. I mean, if you've got the full worked out expression for interpolation memorized, you know, that would get you the same result. In this case, having it here just, it helps me to have it all written out so that I can then just work and manipulate the equation to whatever I need. But if you want to use interpolation, go for it.
Can you quickly explain the steps for the recovery, recovered strain real quick? Sorry.
So when we load this to a point past the elastic region, once I let go, it doesn't just trace back along the stress strain curve. Instead, it goes straight down following a line that has the slope of the elastic region. Okay, so what I need to do is I need to figure out the point that it gets to when it's loaded, figure out both the stress and the strain, and then construct this line right here that has a slope of E1, and then figure out the permanent elongation or the elastic recovery. Again, point slope form is I think one way of doing it.
Okay, that makes sense. So basically just interpolating another line from our original point, pretty much.
I think, yeah, you do have to be careful with what you call as interpolation. But again, at the end of the day, our goal with these techniques is to figure out what this point right here is. Okay,
that makes
sense. At that point, you can figure out your permanent strain and your permanent recovery. Or excuse me,
Okay.
your permanent strain and your elastic recovery.
Okay, cool. Thank you.
Okay. Now, while we're at it, I think there was a question about the spring 2019 exam that has this stress strain curve. So let me go ahead and see if I can pull that up. Unless someone already has it pulled up by chance. Here we are. I think it was question 5 that someone wanted. So take a quick look. Yeah, so this one's actually very, very simple. So you definitely do not want to be overthinking a problem like this. So this is, take a screenshot. Okay. So for this problem right here, we want to figure out what the stress strain, we want to figure out what method we would use to determine the yield stress. Okay, so let me actually zoom in here. All right. So to figure out your yield stress, this is the 0.2% offset method. Okay. This is where we say that if we have a stress strain curve, right, which is nonlinear, you want to draw a line that has the elastic modulus. Okay, so it has a slope of E. And then its starting point is epsilon equals 0.002. So 0.2% strain. Okay. So the intersection point then, that's my yield stress. Problem 5 is from the spring 2019 exam. So if this is my method for determining the yield stress, then it's very easy for me to just start crossing things out. Okay, so this gets axed because the strain is not 0.02. This gets axed because we're not drawing a line that has the same slope as the elastic modulus. We're just going straight up and down. And this does not start at 0.02. Here, we're starting at 0.002, but we're going straight up. So this one's out as well. The correct answer is D, because for D, we're starting at a strain of 0.002, and then we're drawing a line that has a slope of the elastic modulus. So that's it. Very, very straightforward.
So the only reason we can't take B is because it's not at 0.002, right?
Correct. So this would give you a way higher yield stress than we should have.
And how do we know like when to use the offset rule versus like a problem that we just did together 5 minutes ago?
Well, offset rule is just when you're asked to find the yield stress. So in the problem before, we weren't finding the yield stress.
Okay.
0.2% offset is typically when you don't have a linear stress strain curve. Here we have a bilinear stress strain curve. So often what they'll do is they'll just say, take this point right here as the yield stress. So in which case you wouldn't use 0.2% offset. But here, because they are asking for the yield stress and it's nonlinear, you want to be familiar with the 0.2% offset rule.
Sounds good. Thank you.
When it says justify your answer, you don't want to just say the 0.2% offset rule. You want to say, I mean, obviously it's determined using 0.2% offset rule, but then based off of that, how are you eliminating these other choices? Okay, so you could say either by process of elimination, right? And then you say B and C are wrong because they're starting at epsilon equals 0.02 instead of 0.002. And then A is wrong because it's not a straight line with the slope of the elastic modulus. Or you can just go right to D and say D is correct because it starts at 0.002 and it has a slope of the elastic modulus. So you want to have something like that. Okay.
Is it okay if I ask something about the previous problem real quick?
Sure.
So, right here you have like sigma times epsilon. That's like y1 or y minus y1 equals x minus x1, but you just expanded on that.
Where are you looking at?
The line where your cursor is at right now.
Yeah, so this is from point slope form, which is y minus y1 equals mx minus x1.
And is that like an alternative for the interpolation?
So I'd say don't get too hung up on that. I mean, at the end of the day, interpolation, you can derive it from point slope form, right? So, that's one way of thinking about it. I don't remember the interpolation formula off the top of my head because it's been a while since I've done thermo. Let me see if I can grab it real quick.
Because if we did that, then you would have you're looking to find a value in between 0.00225 and 0.03, but
So
then you
in
should
the
also
Yeah, in the interpolation formula, so what they do is they don't have M, they don't write it as M, they just go straight to the substitution. Okay, so I would say again, don't get too hung up on this. The reason why I'm starting with point slope form is just because so everyone can see where I'm coming from.
Okay, sounds good. Thank you.
A quick question, yes or no question.
Yep.
Can we use similar triangles to find the strain?
To find the permanent strain, I'm not sure. I don't think I've ever solved it using similar triangles because I think it's better to just use point slope form, but I guess if we wanted to find it,
No, not permanent strain, just the strain for exerted by force P.
oh, so you're saying what? Figure out something like this. So to draw similar triangles, I guess you'd have something like this. So then this is 50. This would be 477.5 minus 450, so 27.5. And then this would be 0.03, and this would be epsilon minus 0.00225. So we would have epsilon minus 0.00225 over 27.5 equals 0.03 over 50. Let's see if that gets you the same results. I think it should. Okay, I think I made a mistake. Ah, yes, because this is not. That needs to be that. Okay, so that should get you the right answer. And at the end of the day, you can see that we're manipulating the exact same numbers as when we solved it using point slope form. So at the end of the day, it shouldn't matter. Yeah, so
Thank you.
This gets you the same answer. This gets you 0.0175.
Thank you.
$27.5 because the height right here, right, when I draw my similar triangles, I need to take this height right here, but this height starts at 450. So I do 477.5 minus 450. Right? Okay. So let's keep going. Our next problem is a design problem. Okay, so it's not statically indeterminate yet, but we are getting there. So for this, let's take a look. All right, so we have this rigid beam supported by a pin at C and a steel wire AB. Steel has a modulus of 200 gigapascals. We're given all of our lengths. So this right here, it's a length of 6 feet. And then we determine what does W have to be for the NB to be displaced 0.12 inches downward. Okay, so as always, we're going to start with our statics. So draw the free body diagram. So this is W, and then over here we have a cable, which is acting 30 degrees from the vertical, and that cable has a tensile force, which we'll call FAB. All right? So let's go ahead and sum the moments about C. And one nice thing about this is we actually don't need to solve for CX and CY at all. If we just sum for the moments about C, that picks off the value for FAB straight away, and I can move on with the rest of the problem. Okay, so in problems like this, you don't necessarily need to do all three equilibrium equations. Summing the moments about C, we know that the distributed load has a resultant force, which is 10 feet times W. And then that distributed load resultant force has a moment arm, which is just the halfway distance, so 5 feet. And then that's negative because it's clockwise. Then, splitting this up into components, we see that it's only the vertical that has a moment about C. So the vertical component is FAB cosine 30. And then that moment arm is 10 feet. Okay, so then we have FAB times 10 feet times cosine 30 equals W times 10 feet times 5 feet. Right off the bat, we see 10 feet cancels out. So we have FAB equals W over cosine 30 times 5 feet. Okay, remember that this is a design problem, so we want to have everything in terms of our design parameter W. Okay, so even though we have two unknowns here, that's fine. We're going to box this and say that we're good to keep going. Next, we want to draw the displacement diagram. And here it's very straightforward. We're just going to make use of the small angle approximation, right? So I'm going to draw my displacement diagram. Okay. And what I want to do is I want to figure out what the force FAB would be that would produce this elongation, right? So I know that this right here is going to be 10 feet or 120 inches. I know that this right here is going to be, let's say it's 0.12 inches. And then I need to figure out what the corresponding strain of the wire is. So to do this, I'm going to draw a triangle here. This is a bit difficult to see what the angles are, so I'm just going to do this one more time. There we go. Okay. So this right here is point B, this right here is point A, and this right here is point B prime. Okay. And I know that the length of AB is 72 inches because it's 6 feet times 12 inches. So then my task is to figure out what is this length right here. Okay. What is length AB prime? Because I know that to figure out what the strain of the wire is, right? To figure out what delta AB is, that's just LAB prime minus LAB. Okay. So that's my displacement diagram. Any questions on setting that up? So the most straightforward way to do this is to actually add a little bit of extra geometry here. So I can then go ahead and draw a right triangle over here on the side. And then I know that, if I extend this up one more time, since we assume that it moves straight down, I know that this length right here is going to be 6 cosine of 30. And then I can figure out that this horizontal distance is 6 sine of 30. Okay, so 6 sine of 30 is 3 feet. So that means that my bottom length is 36 inches. Okay, then for my side length, I know that the overall height is 6 cosine 30 up to this point, but then I need to add on the 0.12 inches. So I would have then 0.12 inches plus 6 cosine 30, but of course I'd want to do it in inches. So we'd have 72 cosine 30. All right, that gives me the bottom lengths. And now you can see how I've constructed a right triangle, so I'll be able to solve just using Pythagorean theorem. I don't need to spend any time doing law of cosines or any other really tricky geometry like that. Okay, so what we can do is we can say that LAB prime equals the square root of, let's go ahead and first calculate this out. So we have 72 cosine 30 gives me 62.354 inches. 0.12 inches. So then this vertical distance is 62.474 inches. So then LAB prime is going to be 36 inches squared plus 62.474 inches squared. That's pretty straightforward to calculate. Let's go ahead and do that. We find that LAB prime is going to be equal to 72.104 inches. And comparing it to our original length, right? I know that LAB is 72 inches, so this is a reasonable result. If I got LAB prime was less than 72 inches, I would need to do it again because that implies that the cable is getting shorter. My delta AB then is just the difference between these two. So we have 0.104 inches. So that's fine. Now, once we figured out the elongation of the cable, now we see that we're going to be able to tie it back together to the distributed load intensity. Okay, so I want to pause here because this is kind of an important result to get to. Are there any questions on either drawing the displacement diagram or doing any of the geometric analysis to figure out what my delta AB is?
Is it okay if you go over this the second triangle you drew after figuring out your displacement, the red dotted triangle?
Sure. So rather than having to work with triangle ABB prime, what I'm essentially doing is recognizing that I can draw a right triangle that has as its hypotenuse the length I'm looking for, and then as its base and height, distances that I can figure out. Okay, so redrawing that triangle, this is B prime, and this is A, which stays put. This is LAB prime. The base is 36 inches because it's 6 sine 30, right? I'm just doing this right triangle right here.
Mm-hmm.
So that's 6 sine 30. And then this height is 6 cosine 30 plus the added elongation from the beam moving down. Okay, so that's where we have 0.12 inches plus 72 cosine 30. So then plugging in all of my numbers, we get 62.474 inches on the side and then 36 inches on the base.
Oh,
Okay.
that's why you subtracted LAB from LAB prime.
Yes, that's once we figured out LAB prime, we need to relate it to delta AB because I know that delta AB I can relate to the force in the wire. Okay.
Okay, thank you.
Any other questions? All right. So once we've done that, give me 1 second here. Okay. Once we've done that, now let's go ahead and figure out, let's connect everything together. Now, because this is a cable, we know that we're going to probably be in the, well, actually, they tell us here, the wire remains elastic. So that means that Hooke's law applies. We know sigma equals the epsilon, and therefore we can have the lovely relation delta equals NL over AE. So then applying it to this problem, we have delta AB equals FAB times length AB over AE. All right. I'll go and solve for FAB since at the end of the day, that's what we're looking for, right? We know that FAB equals W over cosine 30 times 5 feet. So let's go ahead and see where this takes us. We have FAB equals AE over 6 feet. In this case, I'm substituting 6 feet because I'll see that I'll probably be able to cancel something out. And then that is times delta AB. Then what I'll do is I'll go ahead and just set these two expressions equal to each other. So we'll have W over cosine 30 times 5 feet. So that's fine. Then, let's see, did I make any mistake here? B equals B over L. Okay, so that's all fine. Then finally, we'll go ahead and solve for W. So we have W equals cosine 30 over 5 feet times AE over 6 feet times delta AB is 0.104 inches. So let's do some few unit conversions here. 5 feet becomes 60 inches. 6 feet becomes, actually, we'll leave it as feet. See why we do that in a second. Then I need to figure out my AE is. So they tell us that it's A992 steel, but we're in imperial units. So I will give you that the modulus is 29 megapounds per square inch. So that's 29,000 kilopound per square inch. Okay. Then the area, they tell us that the diameter is 0.2 inches. So for my area, I have that it's pi over 4 times 0.2 inches squared. That is quite simply 0.01 pi inches squared. So then my axial rigidity, which is just the product of those two, is 290 pi kilopounds. Okay. So I'm just multiplying those two together. So we have cosine 30 times 0.104 inches over 60 inches times 290 kilopounds over 6 feet. And we can see, based off of our units, we end up with kilopounds per feet, which at the end of the day is my unit for the distributed load intensity. Okay, so then plugging in all of those numbers, we can obtain our results. So then we have 0.0726 kilopound per feet. Okay. So there we go. That is the distributed load intensity that will cause my beam to move down by 0.12 inches under the small angle approximation.
And the small angle approximation is just the fact that B moves vertically downward. No,
Correct.
no left, right. I see.
Right. In reality, right, if it stays rigid, it would move a little bit like this. But under small
Right.
angle, we can say that it's so close that we can just treat it as if it's going straight downward.
Can we ever not make that assumption?
They'll tell you if you can't make that assumption. Very likely you would be able to make that assumption on the exam because without small angle, your geometry takes way longer.
And you'd end up having to use cosine rule or something.
Right.
Okay, thank you.
Any other questions?
I'm sorry, I'm still a little confused with like how delta AB is being equivalent to like LAB prime minus LAB. Like I can't visualize that.
Say that again.
So delta AB being equal to LAB prime minus LAB, it's kind of hard to visualize that. Could you go over it one more
Well,
time?
the definition of elongation is change in length, right? So delta, right, small delta equals that, right?
Right.
Okay, so we take the final length, right? L final
Oh, I see. Yeah, that
minus
makes
L
sense.
initial.
Yeah.
Okay.
Okay. Thank you.
Any other questions? All right, so I was going to have one of the other TAs solve some problems, but I don't think he's here, so I will just go ahead and solve them for him. So let's go ahead and keep going here. Do we have to take into account that the wire remains elastic? We did, right? So the fact that the wire remains elastic is what lets us write delta equals NL over AE.
If it didn't remain elastic, you'd need some sort of a stress strain curve to actually
Correct.
find the new lengths, right?
Correct. Yeah, so you'd use the tricks that we talked about up here. All right, so let's go ahead and work through this. So Now we're moving on to statically indeterminate problems. And then what's nice about this example is that this is a thermal strain problem. Okay, so thermal strains is fair game on the final. I know we already tested it in the first midterm, but definitely something that we just want to be familiar with. So first things first, we know that we would run through our statics. And interestingly enough, even though there's no loads on here, you still want to draw the free body diagram. Okay. So in this case, I guess if I want to be accurate, I'll draw it stepped. Don't know why I'm drawing the supports actually. Sorry about that, guys. So this is point A, this is point B, this is point C, this is point D. Then we have support reactions, which I can draw them, you know, in every which way I want. Right? Obviously, we know that they're going to have to balance each other out. So RA equals RD. Next, we'll go ahead and write our compatibility condition. So even though it's a thermal strain problem, we still proceed in exactly the same way as we do any other statically indeterminate problem. Okay? So my general compatibility condition is going to be that the sums of the elongations equal to 0 for the case where you have materials in series. And then to get it more explicit, we would say delta AB plus delta BC plus delta CD equals 0. And that's my full compatibility condition. Then, now this is where the fun begins. Okay. One interesting thing to note is that the when we expand this out, right, we're going to have two terms in each one. So the overall elongation is equal to the mechanical plus the thermal. The mechanical is NL over AE. The thermal is L alpha delta T, where alpha is the thermal expansion coefficient. Right? So expanding this out, we have 6 terms that we're going to need to write, 2 for each. So for delta AB, we have NAB times 4 feet over 12 inches squared times the modulus of aluminum plus 4 feet times alpha aluminum times delta T. Now for delta T, I just do final minus initial. So we have 110 minus 70. That tells us that it's a temperature increase of 40 degrees. Plus NBC times 6 feet over, what we'll do is I'm just going to multiply it out so that we don't have square terms in here. For the bronze, we have a diameter of 8 inches. So what I'm going to do is I'm going to have this. Then I have my thermal term, which is 6 feet times alpha bronze times 40 degrees Fahrenheit. And then finally, I have my steel term, NCD times 3 feet over pi over 4 times 16 inches squared times E steel plus 3 feet times alpha steel times 40 degrees Fahrenheit. And all of that is equal to 0. Okay. So we have this big, ugly looking expression here, and then 2 things that we need to do. First, we need to get the material properties in here. So of course, on an exam, they would be given on the final. Here in the textbook, what they do is they have a bunch of the properties tabulated at the end of the book, and then also previous problems give you what those material properties are. In this case, I will just go ahead and write them out. So for E aluminum, we have that it is equal to 10.6 megapounds per square inch. For E bronze, we have that it's 15 megapounds per square inch. And then for E steel, they tell us to take it to be 28 megapounds per square inch. Then For my thermal expansion coefficients, for the aluminum, I have that it's equal to 12.8 times 10 to the negative 6, 1 over degrees Fahrenheit. For the bronze, I have that it's 9.6 times 10 to the negative 6, 1 over degrees Fahrenheit. And then for the steel, I have that it's also 9.6 times 10 to the negative 6, 1 over degrees Fahrenheit. Okay. So once we've done that, the next thing that we want to do is we want to relate the support reactions to the, the internal forces to the support reactions. So very obviously, we would see that regardless of where I make the cut, right, no matter which section I choose, the internal force, the N internal, is going to be equal to the support reaction. All right, so we get N internal equals RA. That tells us that, in fact, NAB, NBC, and NCD are equal. NAB equals NBC equals NCD equals RA. Okay? So with all of that being said, let's go ahead and see if we can manipulate this one more time. So we have RA, and then I'm going to pull out the RA and combine like terms. I'm going to factor out RA and then see what's left. So we have 4 feet over pi over 4 times 144 times 10.6 times 10 to the 6th pounds plus 6 feet over pi over 4 times 64 times 15 times 10 to the 6th pounds. And you can see what I'm doing here is I'm multiplying the inches squared by the per square inch part. That way I can just cancel out some units. Then for my third term, I have the steel. This times 3 feet or plus 3 feet over pi over 4 times 16 times 28 times 10 to the 6th. All of that is equal to the negatives of my temperature change. And then I have what's left is my length and the thermal expansion coefficients. So we have 4 feet times 12.8 times 10 to the negative 6. 6 feet times 9.6 times 10 to the negative 6. And then 3 feet times 9.6 times 10 to the negative 6. So a lot of terms in here, but we can work through it. No, RA equals the internal forces, all 3 of the internal forces, because I don't have any loads in between. My compatibility condition, the fact that it's fixed, that only tells me that the sums of the elongations are equal. It doesn't tell me anything about what's happening in the internal forces. This is a very specific case where because we don't have any internal forces, we don't have any external loads in the middle here. When I make my cuts, I see that no matter what, my internal force is just going to be equal to the support reaction. Okay. So let us go ahead and calculate all of this out. So I will go ahead and just type all this in. Let's see what we get. 4 times 4 times 6 times 6th. Again, on an exam, obviously, this would definitely be a free response question if you're asked to do all of this work, because it's a lot of numbers that you're manipulating. But just a simple thermal strain problem where you maybe only have 2 regions, that's something that could conceivably be a multiple choice question. So making sure I have all my numbers here. The sums of the deltas is equal to 0. Yes, so that is true. We do have that, right? We have that up here.
Oh, I meant like, is it because it's a fixed condition? Is that the reason why we have it?
Have what?
The sum of deltas equal to 0?
Yes, it is. So our compatibility condition, because it's fixed, all the elongations, regardless of what they are, have to sum to 0. So then
Cool,
based on
thanks.
that, we expand it out into 3 terms.
Thank you.
So what I get here is that my coefficient for RA is RA times 1.982 times 10 to the negative 8 foot per pound. And then on my right side, let me go ahead and calculate this out real quick. Yeah, 4 times 12.8 plus 6 times 9.6 plus 3 times 9.6. All this times 6. 40 equal to negative 0.005504. And then that is just feet. Okay. So then I get that my support reaction is go ahead and divide all this out. Get that RA is equal to negative 277.7 kilopounds. Okay. So this is an expected result, right? Because that tells me that in actuality, the supports are crunching my shaft together. And that's expected because the temperature is making it want to get longer. So to counteract it, the walls have to push back on it. So then we say that NAB equals NBC equals NCD equals negative 277.7 kilopounds. Now, if you wanted to find the stresses, right, once we've gotten to this point, we're technically done with our step 3 for statically indeterminate problems, where we are, where we have calculated all of our forces. So then we can do whatever else the problem asks. Would you need to worry about temperature conversions? I'd say no. I mean, they're not cruel, right? I mean, it'd be kind of silly for them to give you a thermal expansion coefficient that's in degrees Fahrenheit and then give you your temperature change in degrees Celsius. If they did, though, right, you know, the conversion from Celsius to degrees Fahrenheit, you should know that just off the top of your head, but it would probably be given to you on the formula sheet. So I'd say don't worry about that. Now, rather than spending any more time on this problem, I will just write what the axial stresses are based on my solution. So once you divide the internal force by the corresponding area in each one, so for example, for the aluminum, we would divide it by pi over 4 times 144. That would get you that the stress is 2.46 KSI. You'll find that for bronze, it's 5.52 KSI. And then for the steel, you'll find that it's 22.1 KSI. Now, as far as whether you mark these with a negative, in this case, it's probably fine to mark it as a negative. So let me just quickly rewrite that. So we would have negative, negative, and negative. And then another thing as well, you can just indicate that these are all in compression. For axial loads, we do differentiate between tension and compression.
I mean, writing it in negative and then writing compression again is redundant, don't you think?
It is redundant, but it's just to be very clear, right? Because if you've done it incorrectly, right, and you end up with the wrong signs, at the very least, having it written as compression, it confirms that you know what's happening.
So it's not like, so if we write negative and compression, they won't think like you're
No,
saying it's
they do
negative
not
compression.
cancel out. The stress
Okay.
really is negative, and the stress is compressive. Those two things are true at the same time.
Got it. Thank you.
But if
Okay?
you were to flip your reaction forces, you would have gotten positive answers and you just write compression.
No, you would still get negative answers. Okay. So if we
Okay.
flipped, because here's what's happening. If I flip the directions, okay,
Mhm.
then you would see how RA would be going to the right,
Oh, and your internal reaction would be
and
negative.
all of these guys
Okay.
would be negative. Okay. So I would
Gotcha.
still extract negative values for the internal forces.
Gotcha.
Okay. Good questions. All right, any other questions?
So, up top when you have like when you realize that RA would just be equal to all the normal forces of the three
Yep.
or I believe the two materials, the three sections. So how did you? I understand that RA equals RD, but if you take a cut through each section, would you end up having all of them equal to each other?
Yes, right. So that's what this expression right here, designates. It's the fact that even if I did it for another region in the middle here, right? If I did it for the bronze, okay, this would be NBC. We still get that the internal force is equal to the support reaction.
Okay, makes sense. Thank you.
How are we feeling on axial loads?
On the right side of the equation, where you have, RA times everything and then equals -40 degrees, are you
Yep.
multiplying all those, the 4 feet times 12.8 times 6 feet times 9.6?
That's
Oh,
what
they're
I-
all addition, okay.
I was running
Thank
out of
you.
room. Spring 2019, problem 4. I think that's a torsion problem, so I'll cover that. I will cover that when we do torsion. Okay, let's see, hour 30. How many problems do I have for torsion lined up? Do you guys want to take a break for a few minutes or go straight to torsion?
Sorry, can you also, the values you got for the stress and aluminum, bronze, and steel, how did you get those values again?
Well, the stress, right? Stress is the normal force over the area. So for example, for the aluminum, it's negative 277.7 kilopounds divided by the area, which is pi over 4 times 144 inches squared.
Okay, thank you.
Okay, let's do a quick break. So we'll break for like 3 minutes. The recording will be available as soon as my computer finishes downloading it. So unfortunately, I can't give any more precise estimate than that. Because it will take a while for it to download, and then to upload it, it's another whole other process. I always promise that it's available by the nighttime. So I would say just stay tuned. And again, I'll send out an announcement for it. All right, let's do torsion. So for this problem right here, this is a kind of intro to torsion. So it goes back to the sort of basics where we're just solving for internal torques and being comfortable with getting our stresses going. Okay, so this is actually a design problem, but the very first thing that we're going to do is we're just going to figure out the internal torsion diagram. So what we're going to do is we'll again draw the free body diagram. And we remember this idea of representing three-dimensional torques in 2D space by just using a double slitted arrow. So based off my right-hand rule, I see that I have to curl my fingers and then have my thumb pointed to the left for this torque over here. So I have 300 Newton meters there. Then for this right term, excuse me, for this center torque, I have 100 Newton meters going like that. And then same thing for this 200 Newton meters. Now, in this case, we can see that the torques already sum to 0, right? We already know that we have 100 plus 200 minus 300 equals 0. But if we cross this out and say that what asked what T was, you would be able to find it using the equilibrium equation. Okay, so we still have equilibrium even for torques. Then we know that we can make our cuts as normal. So call this A, call this B, call this C. We have that this is the internal torque in AB. So we can find that TAB is equal to 300 Newton meters. Then for my right region, I can either keep the left side or the right side. It's a safer bet for me to just keep the right side. So then this is going to be the internal torque in BC. So we have TBC equals 200 Newton meters. Okay. Once you've got the internal torques in all of your regions, what you can do then is set up your internal torsion diagram, right? Here for torques, generally we're just dealing with constant regions, right? So we have 300 here, 200 here, pretty simple to draw, right? We jump up to 300, then at this point right here, we go down to 200, and then at the very end, we go back to 0. Very straightforward. But what is nice about the internal torsion diagram is that then it's very obvious to see where your maximum internal torque is, okay? So based off of this, we see that since the diameter is assumed to be constant for the entire shaft, then all I need to do for my design is look at this region right here. If I had two different diameters, then I would need to set up an inequality for this one, for each one. But by drawing the internal torsion diagram first, then what I can do is write a single inequality that'll take care of this. So remember that for allowable design, right, whatever my allowable value is, that has to be greater than my maximum value. My allowable value is 60 megapascals. And then for the shear stress, we know that we have this torsion formula of TC over J at the outer edge. But then for a solid shaft, we can reduce this to 16T over pi d cubed. Okay, so then what we can say is we go over here, it's greater than TAB times 16 over pi times diameter cubed. All right. Then we'll go ahead and isolate the DAB term. So we have DAB cubed is greater than 16 times 300 Newton meters divided by pi times 60 megapascals. And then what I'm actually going to do here is I'm just going to go ahead and convert the top to 300,000 Newton millimeters. The reason why I'm doing this is because then the bottom, I can express this as Newton per millimeter squared. You can see how Newtons are going to cancel out. So what we get then is that DAB is just the cube root of a bunch of numbers smashed together. And then millimeters cubed. Okay, so this works out. Then we find that DAB is greater than, let's go ahead and calculate this. So we have have this 29.42 millimeters. So then they ask us for the nearest millimeter. So even though the nearest millimeter to 29.42 is 29, we would not be allowed to pick 29 because if we pick 29, I'm breaking the inequality. So then what I have to do is I have to say that DAB min equals 30 millimeters. So you round to the next highest value that still satisfies your inequality. Okay. Any questions on that? It's a very straightforward problem, right? But it's still good to just start with the basics, okay? So we're solving for the internal torques by making cuts, and then we can do allowable design, and then use this little trick right here to make the shear stress expression a little more user-friendly. Okay? People following along so far? This should be mostly review. Well, all of this should be review, I guess. Okay, let's do our next problem then. Actually, let me break for a second and do the multiple choice question on the midterm that someone was asking about. So let me pull this up real quick. I'm gonna have to zoom out here. All right, so we're given this shaft here, and then we have a bonded set of bonded materials with brass on the inside and steel on the outside. Okay, and we're told what's the correct distribution for the shear stress and the shear strain. Okay, now this is multiple choice, so we don't need to spend too long on it. For the bronze, we know that, so tau bronze is going to be equal to 16 TBR over pi d cubed. So we have 16 times 7.38 pound-feet times 12 inches per foot over pi times the diameter. Now it's a little bit difficult to see here, but if I sort of zoom in on the cross-section, right, we have a radius here. The radius is 0.5 for the bronze, and then for the steel, we have a radius of 1 inch. Okay, so then the diameter for the bronze is also 1 inch. So let's go ahead and calculate this out. We get the tau bronze is equal to 451 pounds per square inch. Okay. Now, for the steel, I have to be careful here, right? Even though we're accustomed to using tau max equals TC over J, right? In this case, I have to be careful because this is a bonded problem and I'm interested in what's happening in the middle, right? On the outside, I have tau max equals 1977 for all of them. Okay, so solving for the outermost shear stress is not going to do any good for me. If I instead calculate the shear stress for the steel, but at the center, right, at the innermost point, so tau rho over T rho over J, this will let me pick out which of these options it is. Because here we can see that on these guys, the shear stress is continuous, whereas here it's discontinuous. Okay. So for the innermost shear stress, I have 242.6 pound-feet times 12 inches per feet. Then for my rho, I use the radius, but I'm only looking at the innermost point. So I'd actually use 0.5 inches here. Then for my polar moment of inertia, I recognize that for a hollow shaft, it's outer diameter to the fourth minus inner diameter to the fourth. So we would have pi over 32 times the outer diameter, which is 2 inches, minus the inner diameter, which is 1. Okay, so then let's go ahead and calculate this out. We get that the shear stress at the innermost point is tau steel inner equals 988 pounds per square inch. So this gets to an important point. When you have bonded materials, first of all, the shear stress is not necessarily going to be continuous. In fact, it's pretty much always going to be discontinuous. All right. So based off of that, I can cross out B and C. The second thing that's important to realize is that for a hollow cross-section, right, even though it's bonded materials, the steel just behaves as an independent cross-section, okay? For a hollow cross-section, the lowest shear stress is not 0, okay? The lowest shear stress instead happens at the innermost region where it's something other than 0. For a solid core, the minimum shear stress is 0 because there I'm allowed to evaluate it at the center. Okay, so it's an important distinction here that we have to be careful about. All right, so shear stress is discontinuous. That crosses out B and C. To go a step further, then to figure out between A and D, we just have to ask ourselves, is shear strain continuous? And if you remember back to the definition, or actually the geometric derivation of shear strain, we have this relation right here, right? This just goes back to, if I draw the cross section here, this is where we drew our triangles, right? This right here was dx. We had some gamma in the middle, and then we had d phi as our angle of twist, and then a radius rho. Okay, those two triangles had to be equal, so that gave us this relation right here. Then we isolated it and said d phi dx equals gamma over r. And then d phi dx, now if we apply it to this situation, d phi dx has to be the same for both materials. That's just my compatibility condition, right? Compatibility condition says that phi steel equals phi bronze. If two functions are the same, then their derivatives are also the same, okay? So that means then that d phi steel dx and d phi bronze dx are the same. Since those are the same, I can say that gamma bronze over R bronze equals gamma steel over R steel, right? And actually, if I use the parameters that we're using, the variables that we're using, it should be rho, okay? And now we can see how when we're evaluating it at the interface, we set rho bronze equal to rho steel, so then we find that the shear strain is continuous, right? The shear strain is equal at the interface. So D is out. Based off of this, I conclude that my answer is A.
That's going to be true for any bonded materials like this, right?
Yes, shear strain is always continuous when you have bonded materials.
Got it.
So would it be because of the fact that like when you twist it, you can't make one material twist more than the other since they're
Right,
bonded?
they're bonded. Since they're bonded, they have to move together.
And for the like the discontinuity at 1977 psi,
Well, 1977 psi, that we get just from calculating the shear stress on the outer edge. I'm not bothering with it here because all 4 of my choices have the same value, and I don't have a none of the above choice.
right? But how'd you calculate C? Like, is C just rho here?
No. So we have 2 formulas. This TC over J here is when we're looking at the outermost edge. Okay. When we're looking at at any intermediate point, we have to use T rho over J, okay? Rho becomes C when you happen to be looking at the outermost point.
Oh, so it's only because we're looking at the innermost because it's bonded, basically, right?
Yes, because that'll tell us which of these choices it is.
All right, thank you.
Would we even need to do those calculations, or could we determine the answer by understanding that stress is discontinuous and strain is continuous? In this case, you don't need to do the calculations. You're absolutely right. Okay, you can recognize that we have a discontinuity in stress, but not in strain. But remember that on the exam, you have a none of the above option. Okay, so on the exam, you probably would want to calculate it just to be safe.
And depending on the situation, it's possible that the strain is continuous, right?
Well, strain, no, strain, that is always continuous. The stress.
I'm sorry, stress.
Um,
It would be a rare situation. It'd have to be like constructed that way, but you could
actually, I'm
technically
gonna
make a
answer that conclusively. No, it's impossible, and here's why.
Oh,
Okay, in order for the stress to be continuous, let's evaluate bronze and steel. Okay, at the interface. Okay, so for the bronze, I have T bronze times let's see, times rho, okay, rho inner over J bronze equals T steel times rho I over J steel. Okay, so then my rho i's cancel out. So I have this. Okay, so in order for this to be true, again, if someone's a math major here and they can tell me what the notation is to represent what I'm saying, but just follow along with me, right? I'm saying in order for the shear stresses to be equal at the interface, I would need the ratios of the internal torques to the polar moments of inertia to be the same as well. And I can demonstrate conclusively that this is impossible because for bonded materials, we have the compatibility condition that's TBR times length over GBR times JBR equals T steel times length over G steel times J steel. Okay, so then what I can do is I can then isolate, I can work with each side separately. Then over here, we have that my lengths cancel out. Okay, and now you can see how in order for this to be true, right, once I set the two sides equal to each other, only way this could happen is if my shear moduli are the same, okay? And that's impossible. If they were the same, we're dealing with the same material. So it's not really bonded materials, all right? So yes, conclusively, shear stress is not going to be continuous when you have two bonded materials.
thank you. That clarifies.
Okay. We only need to find tau inner because again, tau outer, the 1977, that's not going to tell us, that's not going to let us narrow down our answer choices, right? We're trying to figure out which one of these is correct. The inner, evaluating the shear stress of the inner region, that will get me closer to the answer.
So is inner right at where the discontinuity happens?
Yes.
Okay.
Okay. All right, so let me do another problem here. Now, this is a power transmission problem, which is one of those special topics that we talked about. And I know, guys, real quick, I know that I'm shifting the window around a lot. It's just so I can get my screenshots of all the problems here. So sorry about that. I know it's a little bit jarring, all the scrolling that I'm doing. All right, so we've got this turbine here, and it develops a whole bunch of power in the shaft. And then we're told that B and C receive an equal amount of power. Then we're told that we're given the diameter of the shaft, and we're told that it has a particular angular velocity of 600 revolutions per minute. Based off all that, we figure out the max shear stress and the rotation of D relative to A. So what this comes down to is that for power transmission, we have this formula here, which says that we can relate the power supplied by a motor or received by a gear, and we can relate that to a corresponding torque by just multiplying it by the angular velocity. Okay, so since we're given the angular velocity, right, we have 600 revolutions per minute. We want to convert that to radians per second. So we do times 1 minute over 60 seconds times 2 pi radians over 1 revolution. So we get that omega equals 20 pi radians per second. All right, that's my angular velocity. And then we can see that when I go to draw my free body diagram, right, we can represent what's happening at the motor and the gears by torques. So this motor right here, that drives the shaft. So that means that it has a external torque, which is going in the same direction as omega, TA. Then B and C are driven by the shaft. So they go in the opposite direction. They extract power from the shaft. Okay, then I have my lengths right here. We've got a smooth bearing at D, so that does not supply any torque. So then this is my free body diagram. From here, I say that, okay, for TA, we have the power of the turbine is 300 kilowatts. So that's 300,000 joules per second divided by the angular velocity, which is 20 pi radians per second. So then the torque supplied by TA is 300,000 over 20 times pi. All right. Then what we can do is recognize that since B and C receive an equal amount of power, then I know that PB plus PC equals 300 kilowatts, and then PB equals PC equals 150 kilowatts. All right. Then, because the angular velocity is constant between all three of these torques, right? Obviously, that's a condition of equilibrium. Then what we would have is we can also make the same argument for my torques. So I can say TB plus TC equals TA. So then TB equals TC equals TA over 2. All right. So then I have TB equals TC equals 2387.3 Newton meters. All right. So that's how you want to handle transmission of power problems. You should be given the angular velocity. Go ahead and figure out what that is in radians per second. And then to figure out the external torques, it's just the power transmission formula right here.
That power transmission formula is not on the formula sheet. Do you think it
It's
would
not
be
on the
given?
formula sheet?
And not the one that I see, the draft final formula sheet?
Well, if it's not on the formula sheet on the actual exam, then you're probably not going to see power transmission problems on there. But in the event that they do ask for power transmission, they would, of course, give you P equals T omega. You know, that would be given to you. And then this is how you handle those problems.
Got it. Thank you.
Okay. So from there, what we're going to do is figure out the absolute max shear stress and the rotation of ND relative to end A. So what I'm going to do is I'm going to quickly tell you that right here, all of these cuts are so basic to make that we don't need to spend too much time on them, right? So we know that TAB right here is going to be 4774.6 Newton meters. TBC is going to be equal to 2387.3 Newton meters. And then TCD is going to be equal to 0 because there's no extra load here, right? So based off of that, I see that AB is my critical region. So then tau max equals 16 TAB over pi d cubed. So then substitute in all of your numbers. My diameter is 100 millimeters. So then that will get me, and actually let me go ahead and again convert this to Newton millimeters. So then my answer here is going to be newtons per square millimeter, so I can immediately express it as a megapascal. And you'll find that this will save you a bit of time doing unit conversions. We get 24.3 megapascals. All right, that's the shear stress. Then for the angle of twist, even though this is not statically indeterminate, right, I can still go ahead and write my my angle of twist as a summation of terms. Okay, so this is going to be the angle of twist of D with respect to C plus the angle of twist of C with respect to B plus the angle of twist of B with respect to A. Okay, then I can expand this out. Of course, angle of twist of D with respect to D is 0, right? So that gets knocked out. Then I have TBC times 2 meters over GJ plus TAB times 1.5 meters over GJ. Okay, then let's go ahead and substitute in our terms here. So for TBC, I have 2387.3 Newton meters. For TAB, 4774.6 Newton meters. My shear modulus is given to be, it's not given here, which means that I need to go quickly look it up. So wait 1 second while I go look in the textbook for it. I think it's something like 29, but I don't want to use the wrong answer here. So let me quickly pull it up. And just so you know, all these properties are in the back of the textbook. So we see I'm looking for, what steel do I have? A992. So A992, what do I have? Structural A992. My shear modulus is 11 MKS, 11 MPSI, right? Okay, that's my shear modulus. So that would be, again, given to you on an exam. Then for the polar moment of inertia, very straightforward. We just have pi over 32 times the diameter to the 4th. And I realize that 11 times 10 to the 3rd KSI is not going to be useful. So let's see what it is in SI units. It is 75 GPa. Okay, that's a bit more user-friendly. Okay. So then let's go ahead and multiply, or actually we can just go ahead and have all these things put together. So angle of twist of D with respect to A is, let's go ahead and do the numerator first. We have 4774.6 Newton meter squared over 75 times 10 to the 9th newtons per meter squared times pi over 32 times 100 to the 4th. And then what we're going to do is we're going to do times 10 to the negative 12th to convert this to meters to the 4th. I'll do the same thing on the other side. So we have 7161.97 over 75 times 10 to the 9th newtons per meter squared times pi over 32 times 100 to the 4th times 10 to the negative 12th. And now we can see all my units cancel out, and I'm left with an answer then that is in radians. Okay. So multiplying this out, let's see what we get. So we have 4774.6 plus 7,000 times 1 over the shear modulus times the polar moment of inertia. That gives me 0.0067 radians. Or converting it to degrees, right? We know the conversion is 1 radian is 180 over pi degrees. So then that gets me an angle of twist of 0.384 degrees. Everything past the calculating the external torques, that's just standard torsion stuff. Okay, the only thing that's special about this problem is the fact that we have a rotating shaft. So then we just relate the power to the torques using this formula right here. But everything else is the same.
So just to have a general like structure in mind of how to set up like a torsion problem, is it like it's always that we need to like just do the free body diagram and then relate the angles depending on whether they're bonded or not. In this case, it has nothing to do with
No, that
to
but I'll cut you off there. So bonded materials is only when it's statically indeterminate. Okay,
Oh,
your
so
first line of attack is the free body diagram. Once you've got the free body diagram, figure out all your internal torques, and then from there, it depends if it's statically determinate or indeterminate. If it's statically determinate, you're good to solve whatever else they're asking for. So in this case, the shear stress and the angle of twist. But if it's a statically indeterminate problem, that's where you go through your motions and set up the compatibility condition and solve for it. If it's bonded materials, that's where you say the angles of twist are equal. Okay.
okay, but you said bonded materials are always statically indeterminate.
Yes. Right. Because think about it. In any bonded material, each one carries its own internal torque, which means that you're not going to be able to solve for everything from statics alone. You need to analyze the compatibility condition.
Oh, I see. Okay. Okay, that makes sense. Thank you.
All right. So we have, this is my angle of twist. Okay, so let's go ahead and do some statically indeterminate problems. And then I have Nishant here is one of our other UGTAs. Nishant, do you have 5-79 ready to go?
I do indeed. Can you all hear me? Am I
Yep, we can
not
hear you.
muted or anything? Okay, thanks.
All right, so I'm going to go ahead and stop it here.
5-79.
So go ahead and share it on whatever.
Now, let me set it
Best.
up real quick. Right.
All right, we can see it. You're good to go.
All right, thank you. So here we have a steel shaft made from two segments of differing diameter. This one here is thinner than this one. And the question is asking us to find the maximum shear stress in the shaft. So obviously, our first step is going to be to draw a free body diagram. So let's do that. Let's put, that's TB, that's, TB, and then the torque at G points this way. So that's D. Let's just say C is there. So this is 5 inches, 8 inches, and this segment is 12 inches. So from our statics equation, we get sum of torques equals 500 minus TB minus TA equals 0. I'll call that equation 1. Since this is obviously a statically indeterminate problem, we have two unknowns there. We then proceed to next step, which is compatibility equations. So in this problem, the angle of twist of A relative to B is 0. And in order to turn this into a useful form for us, we start with segment AC. segment AC. So here is actually just do that. TA, so then in both segments, AC and CD, the internal torque is just TA, so we'll use that. So our first two sections of the compatibility equation are TA L AC over G times AC plus, now for section CD, so again, the internal torque here is once again TA, so we have TA times LCD over G times ACD. Now, for the final part, because it's on the other side of the external torque being applied, we'll draw another free body diagram. Hang on a moment. Sorry about that.
Not just you.
Yeah.
I have problems with that too.
Okay. Let's
Yes.
get back to it. Okay,
pause
so
you for 1 second, Nishant. So question in the chat, yes, because it's fixed on both sides, you have to write that the sums of the angles of twist equal to 0. In this case, you can express that as the angle of twist of one end with respect to the other is 0. Yes, that's exactly it.
so then for segment DB, the beam, the internal torque free body diagram would look something like this. There's TA. There is 500 pound-feet. In this case, I find it's easier to work with pound inches. So then 500 pound-feet times 12 inches per foot is 6,000 pound inches. Let me just remove that and replace it with, oop. Okay, there we are. This is 6,000 pound inches. And so this is the internal torque. The internal torque, we do quick statics. It's T minus TA plus 6,000 equals 0. So the internal torque equals T equals TA minus 6,000. So now we have our internal torque, which in this case is TA minus 6,000 times L dB over G times A dB. And all of that equals 0. Since the shear modulus remains constant throughout, we can cancel that, and that. And then inserting all the values, we get TA times 5 inches over pi times 0.25 inches squared plus TA times 8 inches over pi times 0.5 inches squared plus TA minus 6,000 times 12 inches over pi times 0.5 inches squared. All of that equals to 0. Then algebra occurs, left as an exercise for the viewer, and we get TA equals 720 pound inches. And then plugging this into equation 1 from above, we get TB equals 5,280 pound inches. And now, since the question asks us to find where the torsional shear is maximum, we look at the diagram and see it's either going to be where the rotational moment of inertia is lowest, or where the torsional internal torque is the highest. So that would be either this section or this section. So let's find out shear stress for both sections. So for section AC, we get, excuse me, T rho over J. In this case, rho is C, so it would be TC over J. And in this case, J is equals TR over 2 over 4. Cancel that. That becomes a 3. So I will be using this one for segment DB as well. But in this case, it would be TA, which is 720 pound inches over pi over 2 times R, which in this case is 0.25 inches cubed. And we get that the shear stress in segment AC is 29.335 KSI. So now, in order to check whether this truly is the largest one, we also need to check segment DB. So the shear stress in segment DB due to torsion, DB equals, using this equation again, we get T over pi over 2 times R cubed. But in this case, that equals, once again from equation 1, we get 5,280 pound inches over pi over 2. In this case, the radius is different. It is 0.5 inches cubed. So for segment DB, the shear stress is 26.89 KSI. So for this beam, the section where the maximum shear stress occurs is segment AC, there. Equals max. There we are. Are there any questions?
So in summary, right, you guys see how for these statically indeterminate problems, again, we have our general algorithm. So Nishant started with the free body diagram. He did the statics and equilibrium. Then he wrote the compatibility condition, recognizing that for a fixed case, the sums of the angle of twist are 0. And then he solved the compatibility condition for the torques to get you that extra equation. And then you put all of that together to figure out what the support reactions and internal forces are. Once you've done that,
And
then you can go ahead and solve for whatever else the problem asks for.
yeah, and another way of finding out the third angle of twist in this section, section DB, is you could take a cut and take the right half. The only torsion in there is TB. So you could flip that and then just put a negative sign in front of the third angle of twist, and then you have a 2x2 system that you can then solve. I just solved it this way because it's easier. It's easier for me to solve, and it gets you the same answer anyways.
Where does TB come from? Isn't B just attached to a wall? Or like
TA,
when you take
TA, yeah, TA and TB come from the fact that the beam is fixed at both ends. So you have two reaction forces, one here at A, so this is TA, and one here at B, which is TB.
Oh, so TA would basically be TAC technically, right?
No, they're not the same thing. TA refers very specifically to the support reaction. TAC is the internal torque. They happen to be equal in this case because you don't have anything else going in between. But we distinguish between internal torques and external loads.
Oh, my bad. That's just a wall support. Yeah, that makes sense now. Sorry.
What formula are you using for J at the end?
At B, so for section DB, the formula I'm using for J is just J equals pi over 2 r to the 4th. And I use this form because then I can cancel the r in the numerator and the denominator and use less calculator strokes.
Yeah, I mean, in this case, because it's a solid shaft, I would probably have used the 16t over pi d cubed formulation directly. But at the end of the day, using pi over 2 here instead, that's fine as well. Any other questions? All right, so I'll go ahead and pick it up from here. So Nishan, I did send you another problem as well if you want to have a take a look at that, and I will come back to you.
Sure. Stop sharing.
Okay, so let's pick this up. All right, so the last problem we're going to do in torsion is the other common case that you'll see, which is the parallel case. So we've got solid steel section AB, that's just made of steel. And then for BC, we have steel on the outside and then a brass core on the inside. And based off of that, we got to figure out angle of twists and shear stresses. We're not going to worry about the shear strain. So first things first, we again start with our statics and equilibrium. And now here, I'm going to be very careful to draw the materials carefully. So we have 2 feet here, 3 feet here. And then based off of my right hand rule, I have to curl my hand and have my thumb point to the right. So I would have here 50 pound-feet, which I'll convert right off the bat to 600 pound-inches. Okay. Then I know that TA has to supply, the wall at A has to supply some reaction force, which is going to be equal and opposite. So we have TA equals 600 pound-inches as well. But that's not really the important part, because you might be wondering, okay, well, you know, so far I have solved for everything. But remember that for the parallel case, right, we have to slice through both materials. So then when I draw my free body diagram for region AB, I have that each material carries its own internal torque. So I have TAB bronze and then TAB steel. Of course, for the rightmost region, I know that I can go all the way across. And then even though I'm past the or actually precisely because I'm past the region of bonded materials, now it's very straightforward to find how in this rightmost region, right? This is TAB. So that means I actually messed up. And then these guys right here are TBC. Okay, for TAB, this is just going to be equal to negative 600 pound-inches. So that part's fine. But then over here, I find that TBC brass plus TBC steel equals negative 600 pound-inches. Okay, so this is my equation 1 that I then use with the rest of my steps. Okay.
So you cut it twice, right?
In this case, I cut it twice because I have 2 regions of interest. I'm going to have 2 angles of twist. Right?
Yes.
Okay. So from here, I write my general compatibility condition. The general compatibility condition is that for the bonded materials only, I have angle of twist in the steel is equal to the angle of twist in the brass. Okay. Then we expand this out and have TBC brass times 2 feet over G brass, J brass equals TBC steel times 3 feet over G steel, J steel. Then we'll go ahead and solve for 1 in terms of the other. So we have TBC brass equals TBC steel times a bunch of ratios. So we have first the ratios of the lengths, then the ratios of the shear moduli, then the ratios of the polar moments of inertia. Okay, and what's nice about this is that we no longer have to worry about units. So we have this is times 3 over 2. Then my shear moduli, the ratio is just 5.6 over 11.5, right? I don't have to worry about 10 to the third. And then for my polar moments of inertia, this I do have to be a little bit careful about, right? We know that for the brass is just pi over 32 times the diameter of the fourth. Now here it's a little bit hard to see, but that 0.5 inches is actually the radius. So we have 1 inch to the fourth. But then for the steel, it's outer minus inner. So we have 2 to the fourth minus 1 to the fourth inches to the fourth.
Why are you using 3 feet instead of 2 feet for the steel?
What's that?
Why are you using 3 feet instead of 2 feet for the steel?
Because I'm looking at the wrong region and I made a mistake. Thank you. Good catch. I'm solving it as if this were the fixed case. Yes, precisely. In parallel regions, your lengths are always going to cancel. Thank you. Good catch. Okay, good. So we have that. And then the ratio of my polar moments of inertia are 1 to the fourth over 2 to the fourth minus 1 to the fourth. And now we can see that it's very straightforward for me to solve for 1 in terms of the other. So let's go ahead and do that. So that gives us that the angle of twist in the the internal torque in the brass is equal to the angle of twist, the internal torque in the steel times 0.032464. Okay. So the brass carries way less of an internal torque than the steel does. And actually, if I scroll back up to the problem we did up here, this is not too surprising of a result, right? Here we found that the brass was like, 1/30th of what it is in the steel. And that makes sense because not only is brass a weaker material, but when it's at the center, it has a lower polar moment of inertia. Okay, so that means that the brass has a way greater tendency to rotate, which means that it's going to carry much less of the internal torque. Okay, so there we go. What I can do is I'll actually go and rewrite this so that I don't have quite so many decimals. When you divide that out, you get that it's equal to this. Okay, so then this right here is my third step. Okay, so again, statics and equilibrium, write the compatibility condition, solve the compatibility condition. Plugging it back into my first equation, I have this. So we find that our internal torques are actually going to be negative. And one important thing to note is that for torsion only, we generally consider the absolute value. Okay, so we're not too worried about the signs on these things. Okay, we're going to report the internal torques as negative because that is defined based on a sign convention. Okay, but for the shear stresses, that's where we consider the absolute value. So then for the steel, I would just multiply this by 30.8. Should I be a little bit more careful here? There we go. So those are my internal torques, right? As we did in the problem that Nishant solved, right? You go through all of your steps, and then your goal is to get to the internal torques and support reactions. Once you've done that, then you solve the rest of the problem. Any questions up until this point?
Could you go over the algebra, like where equation 2 is, but the second line of it? So
This
why
right here, we're
yeah,
solving.
why?
Yep.
Sorry, go ahead. Yeah.
No, go ahead. What was your question?
Like TB, we're solving for T for the region TB. Sorry, for the region BC, right? The torsion of region BC, right?
We're solving, well, we're solving for our compatibility condition is only for region BC. So when I expand this out, that's why I have 2 feet on both ends, but then I have different material and geometric properties for each one. Okay. From this equation, I get this just by isolating TBC in the brass.
Oh, okay. I thought we were isolating TBC at steel. Okay, that makes sense.
Well, I mean, at the end, that's what we do because that way I don't have to worry about this big old decimal here.
Yep.
Okay.
Thank you.
So then for the max shear stress, what we can do is apply the torsion formula. So we have tau max in the steel is going to be equal to, well, actually, we have to be careful here. So let's do tau BC in the steel. The maximum shear stress there is going to be equal to 581.134 pound-inches times my C value, which for the outer edge, I'm going to take 1 inch. And then polar moment of inertia is pi over 32 to the 4th minus 1 to the 4th inches to the 4th. See what that comes out to. That gives us a shear stress of 394.6 pound per square inch. Then I'm going to do the same thing in the bronze. Now in the bronze, we have a much smaller internal torque of 18.866 pound-inches. Then my innermost radius, or excuse me, my outermost radius is only 0.5 inches. And then my formula is just pi over 32 times 1 inch to the 4th. Okay, so this should come out much smaller. I'm calculating it here just for sake of going through it, but on the exam, I don't think you would need to calculate this. Okay, we get a much smaller value of only 96. Then that's not the only 2 shear stresses that I have, right? I see that I have this third region over here, but then there I already know what the internal torque is. So I'm good to just use the 600 pound-inches. So in AB, I would say 600 pound-inches times my outer radius is still 1 inch, and then divided by the polar moment of inertia. But now, because it's the entire shape, I just use the diameter of 2 and raise that to the 4th. Okay, so we should see that the shear stress here should be the highest because we have a higher internal torque and a lower polar. Yeah, we have a higher internal question. Okay, let me jump back to that. We use the angle of twist to find the relationship of the two torsions. And yes, so you have to figure out what the internal torques are first before you apply the torsion formula. Okay, so that's what we're talking about, where you get to this step, and then once you've solved for the internal torques, now you're good to solve for things like shear stress and angle of twist. Okay, so multiplying these numbers out, let's see what we get. So I got a bit tongue twisted there. We have a higher internal torque, but a higher polar moment of inertia as well. So we have to see which way this is going to go. So let's see what that gets us. That gets us 381.97 pounds per inches squared. So we see that the maximum shear stress happens in here. Tau max equals 394.6 psi in BC steel. Okay. So any questions on any of that?
Yes, I got a question real quick. So for the shear stress for the bronze, right? So if you go further down,
Yep.
you go. So the radius, is it supposed to be 1 inch or is this 0.5? I thought it was the outermost radius.
It is, but for the bronze, you're only considering the innermost region, right? So if you zoom in on here, the 0.5 inches, that's the radius for the bronze. So we use the radius up here,
Okay.
then we use the diameter on the bottom.
Okay, got it. Makes sense.
Okay. And then since it was pointed out, I guess we can also quickly find the angle of twist. So in here, right, we know that it's going to be the sum of the angle of twist in AB plus the angle of twist in BC. The one thing you have to be careful about is don't just add 3 angles of twist together. You know that the angle of twist in BC for the steel and the brass is the same, so just pick one. All right, so the angle of twist of C with respect to A is equal to phi BC plus phi. How do I have this? So C with respect to B plus B with respect to A. So then I'm going to use the steel just so that I have a constant shear modulus. Okay. Now, when I'm using the steel in BC, I have to be careful because the shear stress, the internal torque is negative. So I have negative 581.134 pound-inches. The length of BC is 2 feet, so 24 inches. The shear modulus is 11.5 times 10 to the third KSI. So we have 11.5 times 10 to the 6 pound per inches squared. Polar moment of inertia is pi over 32 times the diameter, which is 2 to the 4th minus 1 to the 4th. Okay, that's for region BC. Then for region BA, we have the internal torque is minus 600 pound-inches times the length, which is 36 inches. Then go ahead and just rewrite all of our geometric and material properties. So we have now just 2 to the 4th. Okay. Once again, all of our units cancel out. We have pound-inches squared on the top, and then 2 powers of length on the bottom cancel out. So we get that everything becomes dimensionless.
So for just the region BC,
Yep.
can we treat that can we look at it as in like it being a bonded, like 2 materials bonded together just for being BC?
Well, it is, right? That's the whole point of the exercise, is that because they are bonded at BC, it becomes statically indeterminate, and we have this compatibility condition here.
Oh, so first we use the first compatibility condition for just BC, and then now we can look at the whole beam as just 2 separate twist angles and then add them up.
Yes, recognizing that whether I use the steel or the bronze, I get the same results.
Okay, and for BA, are we adding like is the sum of BA? No, they're not zero, right? The sum of BA and CB is not zero.
No, because C is free to twist.
Okay. CA is equal to AB plus BC. Okay, that makes sense.
Okay, so this first angle of twist is negative 8.236 times 10 to the negative 4. And then other term calculating that out.
While you're plugging that in, just a quick question. The radians, the convention for the radians is the same as the convention for the torques, right? So this would be a, looking straight on, it would be a clockwise twist. Just the same as the torque.
Yes, no. Okay, hold on. So looking at it from the left side, okay, looking towards the wall, okay, it's based off of the right-hand rule, okay? So the right-hand rule tells you that the positive angle of twist is counterclockwise, okay?
Right, so in this case, it would be
Yes,
negative, which would
because
be
it's
clockwise.
negative, it would be clockwise. Yes. So you have to do it based off the right-hand rule. The reason why I am careful about using clockwise and counterclockwise is because if you look at it from the other end, well, your clockwise now becomes counterclockwise. So it's all based off the right-hand rule.
Got it.
Okay. Then over here we have minus 0.0012 radians. So then taking the sum of those, we get that the overall angle of twist is negative 0.00202 radians. Or, whoops, technical problem here. Or an angle of twist of negative 0.1157 degrees. Okay, so we have angle of twist of C with respect to A is that. Okay. Right-hand rule, the thumb towards the paper is negative. Yes, thumb into the page would be negative. Okay, so here that would be thumb pointing into the bar would be negative. Okay. Any other questions on that? All right, so that's all for torsion. Let's go ahead and take another kind of 2 to 3 minute break here, and then we'll go ahead and do bending. Yeah, I think this is definitely going to be closer to 4 hours than 3 hours. Is a TI-30 calculator okay to use on the final? Let me quickly look it up. Yes, a TI-30, that's I think the most common brand of calculator that's used. So yes. Okay, so let's go ahead and resume. And now we're going to talk about bending. All right, so for the first problem that we're going to do for bending, it's going to be basically like the question that you had on your second midterm, okay, where it's going to be find the shear and bending moment diagrams, find your cross-sectional properties, find your bending stresses, and then some other small thing, okay? So first things first, the shear and bending moment diagrams. Okay, so for this, we know that we're just going to use graphical method. So before we do that, let's go ahead and quickly run through the statics. So we have here 6 feet. And actually, I'm going to change for the interest of consistency based off of what my units are for the cross-sectional profile that I selected. We're going to change all of these to meters. Let's change that to 3 kilonewtons per meter. So we know that we're going to have AY here and BY here. 9 meters here, 9 meters here. 3 kilonewtons per meter here. All right, so let's see. Summing the moments about A, we know that we're going to have 18 BY going counterclockwise. I'm going to go real fast through this. Then a clockwise moment from a distributed load, which has a resultant force of 27 kilonewtons, acting 13.5 meters away. And then another counterclockwise moment from a 2 kilonewton force acting at the very end. Okay, so based off of that, we have BY equals 27 times 13.5 kilonewton meters minus 12 kilonewton meters over 18. That gets us BY is equal to 19.583 kilonewtons. Then summing the moments about B instead, we have negative 18 AY plus 2 kilonewtons times 24 meters plus 27 kilonewtons times 4.5 meters. So then AY is going to be equal to 48 kilonewton meters plus 121.5 kilonewton meters divided by 18 meters. That gets me 9.416. Actually, 19.417 kilonewtons. Yes, we will do a superposition problem. Okay, so those are my support reactions, and I know that those are okay because if I add them up, I get 29, which is equal to 2 plus 27, all right? So I then come over here, redraw my free body diagram. Go ahead and copy this. All right, so let's go through our normal motions. Now we know that we have to use the differential relations, so I will go ahead and write all those out. We have dv dx equals w, dm dx equals v. Jumps in the shear force are given by point forces, and jumps in the bending moment are given by couple moments. Then we have the integral forms, which goes something like this. Again, by this point, I'm going to go a little bit faster than I did on the second midterm review, because by now this is mostly familiar. So for starters, we know that for the shear diagram, I'm going to start by marking points of interest. So I have things happening at 6, things happening at 15, and things happening at 24. All right. We know that we're going to start off at -2 because this pushes us down. And then we can go straight across because we don't have anything happening in between 0 and 6. Then, so that's going to be equal to V6 to the left. Then V6 to the right equals V6 to the left plus 9.417. That's this relation right here. So that gets me 7.417 kilonewtons. So I go straight up. Once again, I don't have anything happening between 6 and 15, so I just go straight across. Then what I can do is say that this is equal to V15 to the left, actually just V15. Then for figuring out what's happening between 15 and 24, I make use of this relation right here. So I would say that V24 to the left equals V15 plus integral 15 to 24 W dx. So we have 7.417. And then for this integral, because it's a rectangle, I can just take the load intensity and multiply it by 9. So I would have minus 27. That gets me negative 9.583 kilonewtons. Excuse me, negative 19.583 kilonewtons. All right. So then I would come down here, mark negative 19.583 and go like this. Again, just drawing it linear. And then finally, we know that at the very end, we have to be pushed back up by the support reaction. So we see that those are going to cancel out and bring us back up to 0. Okay. So there we go. That's our shear diagram. Then we know that we need to calculate this distance right here, this distance d. To figure out that distance, we'll just make use of the differential relation here. And the trick that we talked about last time is just doing rise over run, right? So I know that my distributed load intensity is 3. Then the rise is just 7.417. And then the run is my d. So d equals 7.417 kilonewtons over 3 kilonewtons per meter. So that gets me a d value of 2.472 meters. So what you would write then is to relate it back to what's happening in the beam, you would say that at x equals 15 plus this, so at x equals 17.472 meters, v equals 0. Okay? So that's our shear force diagram. Now let's do our bending moment diagram. So for the bending moment diagram, let's again mark points of interest. And then right here, we're also going to mark the point where the shear force changes sign, because that's important. Okay. Then we take a quick look and see that we don't have any couple moments anywhere, which is nice. So then let's go through our motions. We know that since we don't have any couple moments, we're just repeatedly applying this over and over again. So it'll be very useful for me to just have all of these areas right here calculated. Okay, so area 1, it's just base times height. So we have 6 meters times -2 kilonewtons. Area 2 is also rectangle, but the base is 9 meters and the height is 7.417 kilonewtons. Area 3 is a triangle, so we're going to have 1/2 times the base, The base, of course, is just my D value of 2.472 meters. And then my height is 7.417. That gets me a a value of 9.167 kilonewton meters. Then for area 4, it's again a triangle, but this time I'm going to do 1/2. And then for my base, I'll take the entire length minus my x value here. Okay, that's another way of solving for this distance. Okay, or I could do 9 minus 2.472. That's fine as well. That's my base. And then my height now is negative 19.583 kilonewtons. Okay. So after all of that, let's see where that takes us. We have negative 63.919. Okay, so that's perfectly good to go. Now that I've got my areas calculated out, applying this relation is going to be much easier because we know that we start at 0. And then for my next point of interest, I say that M6 equals M0 plus my first area. So that's going to be negative 12. Okay, so we go down here, mark this as negative 12, and then it's linear because my shear force is constant. Then my next point of interest is at 15. M15 equals M6 plus 2, which is negative 12 plus 66.753. That gets me 54.753 kilonewton meters. And we again are going to draw a straight line up. Okay, so it's going to be 54.753. Right there. Now we have a triangle, so we see that we have to handle this a little bit more carefully. Calculating it is just M17.472 plus M15 plus 3. So then calculating that difference, that sum rather, is the sum of these two terms. So that's 63.92. And I see that now I need to sort of round it off because this should be quadratic, right? We have linear, linear, quadratic, constant, constant, linear, linear. We have to round it off because at 17.4, the shear force is 0. And by this differential relation, right, if my shear force is 0, my bending moment has a slope of 0. So that's why it flattens out. Yes, it would be concave down. All right. Then for my final term, I go ahead and do M24 equals M17.472 plus 4. We can see that 63.92 and this term over here are basically the same, that we associate any difference to rounding. So we say that it comes back to 0. And once again, we draw it as concave down because my shear force starts at 0 and gets more negative. Therefore, my bending moment starts at 0 and has a slope that gets more and more negative. Okay, so that's a quick review of graphical method. Any questions on that?
So for the last triangle, it starts steep, right? Or it starts at 0 and then it goes steeper.
Yes, because we have a shear force that starts at 0 and gets more negative.
Okay, thank you.
Okay. Any other questions? All right. So then the last thing that we'll extract is the highest positive and lowest negatives. So M max, we see that it's going to be this value right here of 63.92. So M max equals 63.92 kilonewton meters at X equals 17.472. And then M min equals this value over here, negative 12 kilonewton meters at x equals 6 meters. Okay, so those are important as well for when I go to calculate bending stresses. All right. Okay, so once we've done that, then the next step in our sort of exposition would be to calculate the cross-sectional profile. Okay, so I'm going to turn it over to Nishant, who's going to calculate the cross-sectional profile for this particular beam. Ready, Nishant? Nishant, if you're talking, maybe it's just me, but we can't hear you.
Sorry about that. Can you hear me now?
Yes.
Okay, yes, I'm ready.
Okay, so go ahead and take it from here. And do you have the centroid written down separately?
Yeah, that
Start
I
by-
included that. Yeah,
Yeah.
I'll start by calculating that.
Well, actually, I'd say just go ahead, and so the centroid, you guys are probably not going to have to figure that out yourselves just because it takes a while. So go ahead and just draw where the centroid is. We reviewed how to find centroids in midterm 2. So if you'd like to review just finding the centroid, the timestamps for that are on Canvas. So just in the interest of time.
So given this section of the beam, the cross section would look something like this. Drawing is not to scale, obviously, but the centroid is 97.5 millimeters from the bottom. 300 millimeters, 30 millimeters there. There's 30 millimeters there, and another 300 millimeters. So this and these are the dimensions of the cross-section in question. And in order to find the moment of inertia, the basic formula for a rectangular cross-section is 1/12 times base times height cubed plus base times height times the centroid of the section minus, let's see, CS minus the centroid of the actual overall shape. Centroid shape, and then that is squared. And to calculate the final moment of inertia, all one has to do is simply add the moment of inertia for this plus the moment of inertia for the other section, and you get the total moment of inertia. So in this case, it would be 1/12 times 300 times 30 squared plus 30 times 300 times 97.5 minus 15 squared plus 1/12 times 30 times 300 cubed plus 30 times 300 times 180 minus 97.5 squared. And then after just plugging that into your calculator, you end up with millimeters to the fourth. Since this number is kind of unwieldy, we will then multiply it by 1 meter per 1,000 millimeters to the fourth, which then gets you 1.9069 times 10 to the negative 4 meters to the fourth equals I. Any questions?
Do one thing, Nishant. Go ahead and calculate
Yeah.
each one of the rectangular terms separately. So calculate I1 and I2 separately.
Sure.
The benefit of calculating them separately, right, is again, me and Nishant have better calculators than the ones that you guys are going to have. And so what's best is to break this up into manageable pieces, right? The more things that you're smashing together in your calculators, the more likely you are to accidentally type in something wrong, and then, that'll propagate through. Okay.
Yeah, and then let me label the cross section as well. This would be 1, this is 2, equals 1 equals 2. So now you have the cross section. The next step is, of course, to calculate the bending stress. Do you have a moment value for me, Alan?
M max is 63.92 kilonewton meters, and M min is negative 12 kilonewton meters.
And what was the second value, sorry?
Negative 12.
Negative 12, just negative 12?
Yep.
Okay. In order to calculate bending stress, the maximum compressive stress for both these sections would be, so C, or I guess just 1 max would be equal to M times 330 minus 97.5 times 0.001 to convert to meters, sorry, over 1.9069 times 10 to the negative 4 meters to the fourth, which would equal 1219.27 M. And in the case of C2, so 2 would be E, M times 97.5 times 0.001 over 1.9069 times 10 to the negative 4 would equal 511.3 M. So now that we have simpler equations for M, we can move on to calculate. So for the first M, sigma 1 and sigma 2 equal 0.2 equals in this case it would be kilopascals and times 2.795 kilopascals. And then for the second moment of negative 12 kilonewton meters, the sigma 1, sigma 2. Oh, yes?
Would the 77.9 be negative or compressive? Or no?
The
That would
77.9 would in fact be compressive. You're right.
okay. Thank you.
And then since someone's asking, can the numbers be read aloud? We'll go ahead and have them rewritten in a second here. So yeah.
Yeah. So for the second moment, it would be negative 12 be 0.631.27 . 35.9. And again, kPa. So from these four values, we can see that the maximum compressive stress is stress one here. So C max equals 77.93589 megapascals. And so we can also see that the maximum stress and tension is also from here. So it would be max equals 32.682795 megapascals. Significant figures applied as necessary.
So
there we go.
To summarize what's happening, you have to be very careful to, in the most general case, calculate 4 bending stresses. 2 of those are going to be tensile, 2 of those are going to be compressive. And you know that for each bending stress, for each bending moment, you have to calculate it twice. Okay, so you should have a total of 4 values, and then from there you extract your results.
What's the value on the
anyone have-
right hand of the equation for sigma 2? Is that a 971.3 or
this is
571?
let me fix that. Let me write that to be more clear. Sorry. That would be would be that would be stupid. 511.3 m. And I did this because it's just easier to plug into a calculator in case you need to do it multiple times, which in this case I did. Does anyone have any other questions?
So once you do that simplification, you can be sure that only the larger coefficient one is the one that you actually need to use, right?
Well, it depends. It depends because there might be a larger moment on another spot that has that will feed into there, but it might have an opposite sign, in which case it would be in tension or compression. So you have to look at the signs as well.
I guess
The only
I don't
reason,
understand.
yeah, the only
The,
reason that both of these that both of the numbers from this thing were taken is because both of the compressive and tension stresses were maximum at that point. Based on the signs, this might not be the case. So like if the 12 did not have a negative sign in front of it, this would be here and it would be here. And this would be positive, meaning that the maximum compressive stresses would be here. And in this case, yes, this the maximum tension stress would also be over here.
So if the compression and tension, or if the maximum and minimum moments were closer together, then it's possible that you might have a maximum or a minimum on the others through the other calculation.
Right.
Yeah.
Got it.
Any other questions? All right, so I'll go ahead and back and turn it over to me. Thank you, Nishant.
Mm-hmm.
I'll show one other thing quickly here on this problem. Nishant, what did you get for the tensile stress for the negative 12,000?
Sorry, I'm muted. So for the negative 12 for sigma 1, at the top of the cross section, it would be 14.6312 megapascals.
Okay.
And at the bottom, it would be negative 6.1. Oh, you got them?
Yep.
Okay.
All right, so let me go ahead and restart the share here, the screen share here, and I want to show one other thing as well. So, as you saw, right, as what Nishant was doing, you calculate the cross-sectional properties, and then you have two things you have to consider. Your moment of inertia, that gets used in all four bending stresses, and then your C value, that changes depending on whether you're looking at the top or the bottom, okay? So start with each bending moment, right? And then since this is positive, we know that compression happens at the top and tension happens at the bottom. One thing as well, I can't emphasize this enough, so show units. I know here, right, we were a little bit loose on it, just to kind of show the ratios, but it's very important that you show units, and especially it's true here. So I actually left mine in millimeters to the fourth because that makes it much easier to just extract a value in megapascals. At the end of the day, it doesn't matter what you do as long as you're consistent. You have to have either all millimeters or all meters, okay? So any questions on this kind of bending problem here? Okay, so then let's do, let's see. Let's do prismatic beam design. I think there was one on the final exam, the S19 final exam that was good. Oh, one other thing on this problem, right? So one other thing they could ask is, they might give you some allowable values. Let's say that, sigma C allow is greater than, or sigma C allow equals 50 MPa. And then sigma T allow equals 10 MPa, right? So, it's entirely possible, depending on material you're working with, that these are your allowable values. This could be like concrete. Because concrete is way better in compression than in tension, right? Then based off of this, we would say, all right, it is considered safe. It actually is considered not safe in compression because we're exceeding the 50 for the M max, right? So at X equals 17 point, what did I say? 472 meters. And then for the tension values, we see that it's not safe at either location. All right, so the M min happens at X equals 6 meters. Okay, so then our conclusion is not safe in tension or compression. All right, that's something that I've seen them ask on an exam as well as their part 4. Okay. So everyone kind of see the quick analysis that we're doing. Again, if you've calculated your 4 bending stresses and you've been nice and consistent as far as, which one you indicate as tension and compression, your step 4 is going to be very straightforward.
The compressive stress is lesser for X is equal to 6.
What's that?
And the compressive stress is lesser than 50 megapascals in.
Right, but because I have a situation, right, for allowable design, right, we always have this. Okay, so even if it's safe in some parts, right, even though it's safe at X equals 6, it's not safe somewhere else. So our conclusion is that the beam itself is not safe. It doesn't matter if one part of it's safe, but if the other isn't, then it's still going to fail.
Oh, so the bottom line applies for the entire thing. I thought it only applied for M
When we
min.
do allowable design, if they asked you, if they were very specific and they said, is it safe at X equals 17 and is it safe at X equals 6? Then you would say, okay, in compression, it is safe at X equals 6. But generally they don't ask that because what does it matter if it's safe at X equals 6, right? If the beam is going to break at any point, then you cannot use that beam, right? So it's important to consider things holistically.
Got it. Thank you.
Okay, so let me do the prismatic beam design problem from spring 2019. Okay, so in this problem, what we have is we already are given the shear and bending moment diagrams, And then we're told with an allowable stress of 135 megapascals, what shape are we going to use? Okay, so first things first, we recognize that we can go straight to our allowable design formula, which is sigma allow is greater than sigma max. Then for sigma max, we know that that's equal to MC over I. But then we have this property called the section modulus, which we remember it's defined as I over C. So then we can write sigma max equals M over S. And then we have sigma allow is greater than M over S. Okay. So based off of this formula right here, we need a few things. We need sigma allow, but that's usually given. And then for our value for M, this is where we look at our bending moment diagram. So if the bending moment diagram were not given, you would need to find it yourself. Okay. Based off of this, we see that the maximum bending moment, whether I consider the absolute value or not, is 34.64. Generally, when we do prismatic beam design, we're not going to differentiate between the highest positive and lowest negative, because generally these shapes are symmetric, which means that our tension and compression would be the same. Therefore, we consider the absolute value, so we do 34.64. And then we manipulate this and say that our required S is basically M over S, where M is M max. Okay? Whoops. All right, so we have this, and then let's go ahead and substitute. So our required S value is 34640 Newton meters over 135 megapascals. What I'm going to do is I'm going to convert this to millimeters. That way I have whatever this value is divided by this is just millimeters cubed. Okay, so then this will give me, if I divide that out, 256.6 times 10 to the third millimeters cubed. Okay, so remember that in your prismatic beam design, you first have to get a numerical value for our S required. Okay, now, once we're at this point, we look at all of our choices, okay, and we see that right off the bat, we can eliminate B. Okay, we eliminate B because its S value does not meet this criteria. For all of the other ones, right, in order to break the tie and figure out which one is the most appropriate, all of these are satisfying our constraint. So then what you look at is the second number, which is the weight, okay? Based off of this, we see that section C, the W310 by 24, that has a weight of 24 kilograms per meter, which is the lowest of the others. So then I pick C as my answer. So as you can see, this problem took like only a few minutes to do. You don't want to spend any longer than this on this than is needed. Okay. So in prismatic beam design, go ahead and draw the bending moment diagram if it's not already given. Figure out what your required section modulus is. And then if it's a multiple choice question, right, see which candidates satisfy this inequality. Then among those candidates, you pick your final answer based off of which one has the lowest weight. And that's also how you would read the tables in a free response question, okay? So I think I did an example of that on the second midterm as well. But if you were not given these particular candidates and you had to find it yourself, that's where you would look in Appendix B and Appendix C.
If that if the max and min were not the same, would you just take the largest absolute value?
Correct, because generally for prismatic beam design, we're not going to differentiate between tensile and compressive.
Got it.
Okay. All right, let's do some superposition problems. Trying to think, how many do I want to do? S is the section modulus, yes. Okay, so S is this property that's just defined as the moment of inertia divided by our C value. Okay, so let's take another super brief pause and we'll go ahead and reconvene at like 2:30 while I go ahead and find some superposition problems to do. Hopefully the review is helpful so far.
Super helpful. Thank you so much, Alan.
No problem. Okay, so we're gonna kind of resume here. And pull up the, oops, closed out of it. Let me actually get my appendices ready because we are going to need those. So a few more seconds here. It's ready to go.
Can I just ask a general question about superposition?
Sure. I'm gonna
So,
do some theoretical review for statically indeterminate beams and bending, just so you know. But superposition in
Okay.
general, what's up?
I guess, you know, I'm conceptually struggling with, like, do you have to create equations for the entire beam at once, or can you break the beam into sections and use equations for each section?
You have to do it in I mean, when you say an equation for the entire beam, that equation is going to be piecewise, right? So you're not going to be able to write one single equation, because the whole point of our kind of techniques is that the equation is very much different for each region, right? If your loading changes, your bending moment changes, and if your bending moment changes, then your deflection equation changes.
Sure. All right. Maybe let's go through a problem, and I can have a
Yes.
more specific question then.
Yes, let me start with this one right here. Actually, no, I want numbers. Okay, so let's take a look at this problem right here. Oops, I need to screen share. Okay, so we're going to take a look at this problem right here. And what we're going to do is we're not going to work with just this beam. We are going to add a distributed load acting all the way across. That distributed load is going to have an intensity of 300 pounds per feet. Okay, so with superposition, the idea is basically this, right? You want to identify if it's one of basically three main configurations, and there's only two that you're pretty likely to see on the final. You have this one, which is simply supported. You have this one with a fixed support. That's the cantilever. And then the third one, which you're probably less likely to see, but it can happen, is the overhang. Okay, so that's where you have something like this. Okay. Generally, we're going to consider cantilevered and simply supported beams because the overhanging ones take a lot longer to solve. But when you recognize that your beam is simply supported, what you can do is you can look at your superposition tables, right? So if I bring in some superposition tables, we see that for a single load, okay, for a single load, the elastic curve and deflections and slopes, those are given, okay? Those are already tabulated for us. Even though this, we don't have the table for it, the whole point is that we can split it up into the superposition of two beams, and then each beam carries a single load. Okay, so we can split this up into two beams. And then we have 600 pounds here on the other one. This would be 12 feet. This would be 8 feet. And then 4 feet. Okay. Then let's say that I wanted to calculate the deflection right in the center. Okay. So Actually, let's go ahead and just get the elastic curve throughout. That's fine. Or I guess they don't have the equation here. So we'll worry about just the left side for now. Okay. So for 0 is less than x is less than 8 feet. What we can do is we can say that v total equals v1 of x plus v2 of x. And then for each one, we grab the corresponding equation from the tables. So for example, we would say that v1 of x, this is for the distributed load, v1 of x is going to be equal to negative wx over 24 ei times x cubed minus 2l x squared plus L cubed. And then V2 of x is based off of my point force. So I would then use this equation over here and say negative PBX over 6 EIL times L squared minus B squared minus X squared. But of course, written in these forms, it's useless because these are just copied from the tables. We need to apply them based off the values that were given. So for example, in 1, we have that W is equal to 300 pound per foot. I'm going to change this actually. Let me write that in inches. Okay, so we're going to have, let's see, which way is going to be faster? That's given in inches, that's given in inches. Yeah, let me go ahead and work with only inches. Okay, so 300 pound per foot to pound per inches. Let's do, we're going to have times 1 foot over 12 inches. So 300 over 12 is going to be 25. Then I know that E is going to be 1500 KSI or 1.5 million pound per inches squared. My moment of inertia, I know that I can calculate my moment of inertia based off the cross-sectional profile. So it's just going to be 1 over 12 times 3 times 6 cubed inches to the 4th. So let's go ahead and calculate that out.
Why are we using elastic curve if we're trying to find deflection?
Here. We're not doing the problem that's written in here. We're doing my problem. Basically, I want to, we've been doing a lot of just finding it at a particular point. Right now, we're just reviewing superposition tables to get the entire elastic curve. We'll talk about how you'd get the max deflection in a second here. Okay. Does that answer your question?
Yes, thank you.
So we have the moment of inertia is 54 inches to the 4th. And then finally, I need the L. Now the L is the entire length of the beam. So I would take 12 times 12 is 144 inches. Okay. So then now I can write V1 of X equals negative 25 pound per inches times X over 24 times a whole bunch of stuff. So we have 1.5 times 10 to the 6th pound per inches squared times 54 inches to the 4th. And then all that times x cubed minus 2 times 144 inches times x squared plus 144 inches cubed. Okay. And we can see that based off of units, right? Again, you know how much of a fan I am of checking my units. 1 pound per inch cancels out. So I'm left with inches cubed on the bottom. And then over here, this entire expression will be in units of inches cubed. So then I'm left with just inches on the top once I plug in x. Okay. So then multiplying all the numbers out, we have, so negative 25x over 1944 times 10 to the 6th x cubed minus 288 x squared, and then plus 144 cubed, which will leave as 144 cubed. Okay, so that's V1 of x. Then for V2 of x, I need to do the same sort of process Let me do this. I need to do the same process that I did for 1, where I then assign values, okay? So in 2, I have that P is equal to 600 pounds. And then I have that my B value, now they tell us in the tables that B is the distance from the right side. So with 4 feet, I take B to be 48 inches. And my L is still 144 inches. And my EI I can just copy over. Okay. So then let me take my V2 expression. V2 of X equals negative 600 times my B value is 48 times X over 6 times 1.5 times 10 to the 6th times my moment of inertia times my length. Now notice I'm dropping units because now I've established that I'm working with just pounds and inches. So I don't need to worry about that. Then I have 144 squared minus 48 squared minus X squared. Okay, so I've got 2 expressions here. And then what I can do is I can combine them and say that my total elastic curve equation is just the sum of those values.
Sorry, this is still valid between 0 and 8, right? What do we do
Yes.
if we want to know what happens beyond 8 and up to
Well,
the very end of the beam?
So I'll tell you right now, this is a shortcoming of the tables. Okay, so the table does exist for that has the elastic curve between 8 and 12, right? So if you were asked to find this, you would be given a table that has very likely that has the deflection between 8 and 12. I'm not sure why it's not included here.
I gotcha, thanks.
Okay, it's especially funny because here they bothered to do it for both sides, but they didn't do it for up here. So
There's no way to do an L minus X substitution to
okay,
find the value.
Very important point. No, you cannot do that here because it's not symmetric. Okay, if P were right smack in the center, then yes, you could do an L minus X substitution. Okay, but only if it's right in the center and only if it's simply supported. Okay, if it's cantilevered, you can't do that because again, a cantilever beam is not symmetric. Okay.
Couldn't you switch the A and B values and then also do the L minus X and then it would be
yeah, I guess you could. But again, right, you know, the table, I'm telling you, the table already exists. Let me just pull it up here. Right. So there's no point in really spending all this time when very likely the table would just be given to you. Let me see.
Okay. I would much prefer to just read it off the table than do that anyway. So
yeah, let me pull this up. I know I have them somewhere. Gosh. I really need to reorganize my folders. That's what's happening.
it's all right. If you're confident that they will give us the equation for that portion and we won't have to work it out somehow, then
I mean, again, I'd be surprised because again, on the exam, it's very likely going to be a statically indeterminate problem, right? So you're not going to be looking at the elastic curve anyways.
Okay.
Yeah, there's your intermediate load. Okay. So there are some tables which are better than the Hibbeler tables, which give you the equation on both the left and the right side. Okay. So for my V total, going back to this, then I know that it's just the sum. Let me go ahead and move this out of the way. My V total is just the sum of those two terms. Then we have 144 squared minus 48 squared minus x squared. And this is something I could plot, and this would give me the deflection at any point for 0 is less than x is less than 96 inches. Okay, and I'm writing it in inches here because x has to be expressed in inches. Okay, so that's the idea with superposition. Whatever value you're looking at, okay, you can just split up your beam into a bunch of simpler beams that each have a single load, and then get your necessary information from your tables. Okay, after that, it's just a bit of algebra. All right. Any questions on that? They are added. So the tables, this is an important point right here. So the tables take V to be positive going up. Since the loads are pointed down, we expect to obtain negative values for our deflections. Okay, so when I extract them from the tables, I'm making use of the negative, and then I'm adding these two guys together. So that's why they both show up as negatives. Yep. All right, so far more common then is using this to solve statically indeterminate beams in bending. So let's go and let's do some theoretical review first. Okay, so statically indeterminate beams in bending. Okay. In bending, we have, let's consider the situation where we have a cantilevered beam, but we've got a stupid roller that's stuck on the end of it. Okay. So if we were to draw the free body diagram, we know that this is going to be statically indeterminate because I have 3 support reactions over here and 1 support reaction over here. So only 3 equations for 4 unknowns. Okay. But what statically indeterminate procedure says is that you can use our tables to figure this out. Okay. Let's say that this has a length L, and then let's say that we have a point force P in the middle. What you do is you identify the redundant support. Okay. So the redundant support in this case is the roller at x equals L. We identify the redundant support based on what's keeping us from being either a cantilevered beam or a simply supported beam. Okay. Here, if I got rid of the roller support, I have a cantilevered beam, which is statically determinate. Okay. So then based on the redundant support, you want to split up your beam into 2 other beams. Your first is your primary beam. Okay. Your primary beam has everything except the redundant support. Okay. So I would then draw this with a point force P in the middle. And notice, so this has everything except redundant support. So let me write that out. All right. And then if that has everything except my redundant support, then based off the principle of superposition, the second beam that I'm going to draw has only the redundant support. Okay. But now I'm going to express my redundant support based off of the support reaction. So I would call this like By. This were A and B. Okay. Now you can recognize that both of these beams are going to be statically determinate, okay? Which means that you can use the tables on both of them, right? Then you would write the compatibility condition, okay? In this case, your compatibility condition, you're almost always just going to evaluate it. And actually, I don't want to use any imprecise language here. I can't think of a condition where you're not going to evaluate at the location of the redundant support. Okay, so you're going to say evaluate at redundant support. So since we have a redundant support at x equals L, I would say that at x equals L, then I have some value for V. And because it's a roller supports have a deflection of 0. We would say at x equals L, V total equals 0. Then you can see that for both of these guys, I can write the superposition tables for them. So I would say that working on my compatibility condition, V1 max this is 1 and this is 2, V1 max plus V2 max equals 0. And then V2 max, this is going to have my By in it, but it'll be the only unknown that I have. So then based off my compatibility condition, I'll then be able to solve for By. Okay, so that's your general procedure for statically indeterminate beams. You want to identify the redundant support and then split up your beams into something that has everything except the redundant support, and then a beam which has only the redundant support. Okay.
You're only using the max part because the deflection at B is the maximum deflection. In some other cases, it would just be the deflection at that support, right?
Correct. So yeah, let me be a little bit more precise here. So it's a V1 at x equals L and V2 at x equals L. Okay. All right, so let's do our first statically indeterminate problem. Wait, no, I didn't want to start with that one. We'll do that one later. Give myself some more room. Let's do this one. There we go. That one's better. Okay, so what we're going to do here is we're going to go through our steps. Right off the bat, we see that we have a redundant support at B. So I'm going to immediately split this up into my primary beam and my auxiliary beam. Okay, my primary beam is going to be simply supported, and it's going to have 2 loads on it. It's going to have 5 kilopounds here and here, located 4 feet. This is going to be 12 feet, and this is going to be 4 feet. Plus, so that's my primary beam. And then for my auxiliary beam, I see that I have to have everything except, I have to have just the redundant support, I should say. Okay, and this is located at 10 feet. So right in the center. Now notice, my primary beam has multiple loads on it. Okay, that's fine. Once we have it statically determinate, we can then split this up further into the superposition of 2 more beams. Okay, so we could split this up as one beam, which has a load at 5 kilopounds. A load at 4 feet. And then one beam, which has a load at 16 feet. Okay, so this can be done after the fact. Okay, this right here, this is all optional. Okay, for starters, I think it's good to just get in the habit of starting with 2 beams. Okay, because you can recognize how this by itself, you can absolutely use your tables on, even though it'll just be in terms of By. Okay, so really get into this habit. Once we've split it up, we're then going to use our superposition tables. Okay, so we'll call this beam 1 and we'll call this beam 2. Now, in this case, the compatibility condition that I write is going to be at x equals 10 feet. We say that my V total is going to be equal to 0. So then I need to evaluate V2 at x equals 10 feet. To do that, I'll go ahead and look at my superposition tables. So we have here, for the load right in the center, we can just use V max. So V max is equal to negative PL cubed over 48 EI. So we'd say that V2 equals positive By times L cubed over 48 EI. And we're switching it to be positive because By is going up, right? So then expanding this out, this is going to be By times 20 feet cubed over 48, and then we'll leave the EI as is. Okay. Now, for beam 1, you would ordinarily then split this up into the superposition of 2 beams. All right, because we know that we have the table available for the case of an intermediate load, right? we have the table right here, so we could just do this twice, okay? However, I'm going to cheat and recognize that the table does exist for twin loads already. So let me go ahead and pull that up. No reason to give ourselves any hard work here. Let me find the twin loads. Here we are. Okay, so I have this lovely table right here for the case where we have twin loads, which are symmetrically placed. Okay, so in this case, we know that Y max is going to happen right in the center. Okay, and then F right here, F is pointed down, which means that I have to be very careful as to what sign I'm going to end up with here. Okay, so let's go ahead and evaluate Y max. V1 at x equals 10 feet is going to be equal to 5 kilopounds times my A distance. Now I know my A distance is just going to be 4 feet over 24 EI times 4 times 4 feet squared minus 3 times my length. Now my length is the whole thing, so I know that there I can just use 20 feet squared. Okay, so I've used my tables to figure out what V1 at x equals 10 feet is and V2 at x equals 10 feet is. Now I combine them in my compatibility condition. Okay, so the first thing I'll do is I'll simplify this a little bit, so it's a little bit more user-friendly. So V1 at x equals 10 feet. We're going to have 5 times 20 kilopound feet. And then my term in parentheses is going to be 4 times 4 squared minus 3 times 20 squared. Okay, so then I have 20 times that over 24. I get this is going to be negative 22720 kilopound feet cubed over 24 EI. Okay, and then I'll do the same thing up here. V2 at x equals 10 feet is going to be equal to 20 cubed over 48. So we have 8,000 BY, or 8,000 feet cubed times BY over 48 EI. For the first beam, we wrote at x equals 10, V total equals 0. So it's not for the first beam. This is my compatibility condition. Okay, so I'm saying that when I put these two beams together, even though separately I don't have 0 deflection at x equals 10, when I put them together, because there's a roller support at B, the overall deflection has to be equal to 0. Okay? All right, so these are my two expressions that we can see how the units cancel out nicely. BY is just going to be in terms of kilopounds. And then another thing I see is that we again obtain the correct sign, okay? So here they take Y to be positive going up. We know that for V1, my loads should push my beam down, so I get a negative deflection in the middle, all right? So applying compatibility, we have negative 22720 kilopound feet cubed over 24 EI plus 8,000 feet cubed times BY over 48 EI equals 0. So then if we solve for BY is going to be equal to 48 EI over 24 EI. Nice thing about this is that when you have a roller support, EI always tends to cancel as long as it's constant. Okay, so then we have times 22720 kilopound feet cubed over 8,000 feet cubed. So then based off all that, I find that BY is, please, 5.68 kilopounds. All right. So then once we've done that, once we've identified the actual value for our redundant support, now you can go back in and do all of your statics as normal, okay? So once again, we start off by splitting it up into a primary beam and an auxiliary beam, write the compatibility condition, evaluate it at the redundant support, and then make use of some tables to figure out, to then work your compatibility condition. And then after that, some algebra to get your final answer. Any questions on that? All right, I know we're past the 4-hour mark. I've got one more problem that we're going to do, and that's the one with the flexible support. Okay, so hang in there, guys. We are almost done. So here we are. Now we can see that we've got the cantilevered beam, and then we've got a wire at the very end. Okay, and then based off of this, we have to figure out the force developed in the rod. Now, this is a very important case of the flexible support, right? From here, we're still going to go through our standard steps. So let's start by splitting this up. We know that we're going to have the cantilevered case. Let me just draw the quick representation on here. Length of 10 feet overall, 8 kilopounds here, and then 5 feet here, okay? To split it up into our primary beam and auxiliary beam, we recognize that this wire is redundant. If I didn't have the wire there, I'd be able to have a cantilevered beam, okay? So my primary beam just has the point force in the middle. And then my auxiliary beam, which has just the redundant support, that has a force which we'll call FBC acting at the very end. Okay. Next, we write our compatibility condition, and we again know that we're going to evaluate it at the redundant support. So we're going to say that at x equals 10 feet, we have that one side is going to be V total. But whereas before I was able to say that V total is going to be equal to 0, here I can't do that. Here V total is not necessarily going to be 0 because this is a wire. The wire itself deforms, okay? So instead, for a flexible support, what you will tend to do is write it as delta, or in other words, delta wire. Okay, now we can see what our approach is going to be. We're going to have the total deflection on the left side of this equation. That's going to come from our tables. And then the right side, this is typically going to come from NL over AE, right? The elongation of this wire can be written as NL over AE. And we'll see how even though it's not equal to 0, FBC will still show up. So that'll be my only unknown. Okay. So this is our compatibility condition for the flexible support. And we did a lot of examples of this in class, right? On recitation, you saw how this can go even further and be a problem with a gap as well, right? Any information about the gap that would go here on the right side. Any questions on setting up the compatibility condition?
Since the delta for the wire is positive going downwards, we would like multiply the entirety of the left-hand side with a negative sign, right?
Correct. So that moves us to the next point. Once you've written down your compatibility condition, you have to be very careful about your signs. Depending on the tables that you're given, you might not have to worry about this. But here, we know that the entire beam is going to tend to move downward, right? Because this flexible support, that doesn't do anything on its own. It just tries to counteract the deflection a little bit. So since the entire beam moves down, I know that the V total is naturally going to assume a negative sign, okay? But delta wire, if I write it as NL over AE, right? Or put in other words, you know, it's going to be FBC times 8 feet over AE. FBC is tensile, right? FBC has to be positive Otherwise, the whole assumption would be thrown off, and this would negative FBC would imply that the wire gets shorter, which is obviously not possible here. So to fix this, you would have to recognize that since delta wire naturally will assume a positive value, you need to throw on a negative. So then the compatibility condition that you work with would be V total equals negative FBC times 8 feet over AE. Okay, so it's very important that you take care of your signs when you're dealing with flexible supports. Does the compatibility equation always go to redundant support that prevents the beam from being a cantilevered beam? It goes to the redundant support, but if you have a simply supported beam, right? So up here, we had a simply supported beam. We were evaluating it at the center because that's what was keeping us from being simply supported, right? You evaluate it at a point where the deflection is known, okay? We don't know the deflection anywhere else on this beam. We know that it's 0 at A and C, but that's useless. That's trivial. We know that it's going to be 0 at B because of a roller. Here, we evaluate it at the end because I can write an expression for the elongation as delta equals NL over AE. So yes, you're going to evaluate it where the redundant support is. Make sense? All right. So this is my equation that I'm working with now. So then let's extract our information from the tables. We need 2 tables here. Okay, so this is my right side. I'm going to leave that alone. For my left side, let's call this as case 1 and call this as case 2. We have V1 plus V2. For V1, evaluated at x equals 10 feet, okay, V1 is the case of a point force in the middle. So I'm going to go over here. Helpfully, the maximum deflection occurs at the very end. So I'm good to just borrow this. But if it were at any other location, that was where my redundant support was, like let's say that my redundant support was here, then I would use the elastic curve instead. And I would plug in for my x value, for instance here, x equals 7.5. Remember that the deflection is always just a special case of the elastic curve. So for V1 at x equals 10 feet, I would have negative 5 times PL cubed over 48 EI. My P value is 8 kilopounds. My length is 10 feet, which gets cubed, and then over 48 EI. Now, E, they tell us that it's 29,000 kilopounds per square inch. And then the moment of inertia, they tell us that for the beam about its neutral axis, it's 475. But now that you guys know how to calculate cross-sectional properties, right, they could just very easily give you the cross-section of this beam and then tell you, okay, figure out the inertia, moment of inertia yourself, and then find me the deflection, okay? In this case, it's given, so we're going to just keep going forward. Then for V2, evaluated at x equals 10 feet, this one is a point force, but it's happening at the very end, and it's going in the positive direction, which means that I would need to flip the sign here. So I would have positive FBC times the length cubed over 3 times the EI product. Okay. Then up here, let's go ahead and quickly work out what the area is. So they tell us that the area of this wire is a 1/2 inch. Rod, I should say. So area is pi over 4 times 1 over 4 inches squared. So pi over 16 inches squared. Okay. So then let's put it all together with this compatibility condition. We have negative 5 times 8 kilopounds times 1,000 feet cubed over a denominator, which that I am going to calculate. is going to be a very big number.
Would you recommend solving this term by term?
Yes. So we're gonna talk about that. So we have 661.2 times 10 to the 6th. And this is kilopound inches squared. Okay, that's my V1 plus my V2. So I have FBC times 1,000 feet cubed over the denominator, which should normally be just this divided by 16. Okay. So those are my first two terms, and then that's equal to, on the right side, negative FBC times 8 feet over pi over 16 inches squared times the modulus, which is again 29,000 kilopounds per inches squared. Okay. So from here, you can now see that FBC is my only unknown. So it's just a bit of algebra to get the final answer. However, when you're at this point on your exam, don't try to do a ton of algebra and then have one massive term that you throw into your calculator. If you do that, it's very likely that you make a mistake. And I know this because that happened to me a bunch of times when I was trying to get one big term. It's much easier to just calculate numbers and coefficients on all three of these guys, and then from there, do some more algebra. Okay, the fewer terms that you plug into your calculator at once, the better. All right, so to do this, the first thing that we're going to do is we're going to multiply this by a conversion factor of 12 inches per foot cubed. Question, isn't FBC supposed to be positive on the right side? No, it's not, because remember, right, we have to be consistent with our signs. If FBC is positive, which it has to be, that has to correspond to the beam moving downward, okay? But since my tables assume that the positive direction is upward, that means that I have to throw on an additional negative myself so that everything is consistent. If I didn't do that, I would probably get a negative value for FBC, which would then fly right in the face of the idea that this is a rod, okay, that's getting longer. Okay, so you have to be careful with the signs here. Does that answer your question? All right, so for this first term, we have 5 times 8 times 1,000 times 12 cubed divided by 661.2 times 10 to the 6th. We see that now I get inches cubed kilopounds over inches squared kilopounds. So this term is just negative 0.10454 inches. Then this next term, I'm again going to have that same conversion factor. But this is going to be a coefficient now. So I'm going to have plus FBC times some big number. This is going to be plus 0.041815, but now I'm going to have inches per kilopound. Then on the right side, this is a bit simpler to calculate, but I still need to do a conversion factor. So we have negative FBC times 8 times 12 over pi over 16 times 29,000. So we have 0.01686. And again, we have inches that cancel out on the bottom. So we have inches per kilopound. Okay. So again, calculate each one of these terms separately in your calculator. Don't throw them all in at once. Finally, now I can go ahead and solve for FBC. So I see that FBC times 0.041815 inches per kilopound plus 0.01686 inches per kilopound equals 0.10454 inches. And now I can solve for FBC. actually, we can go ahead and calculate that denominator pretty easily. That denominator is 0.05867 inches per kilopound. So you can see that the kilopound jumps up. My final answer then is going to be 1.782 kilopounds. All right, so FBC is a positive value, just as we expect, and it's going to counteract the deflection of my beam. Okay. So with a flexible support, we still go through the superposition with the primary and the auxiliary, but the compatibility condition gets a little bit more complicated, where now we're using the axial elongation formula instead. Okay. Any questions on that? Scroll down to the final answer.
It seems to me like it would have been a little simpler to cancel out the E values since they're in the denominator of all of these.
Yes, you could have. You're right.
Okay.
You're absolutely right. In this case, I just decided not to do that, but you absolutely could. One thing, though, is that there are cases where they'll be cruel and not they as in the professor saying that you're whatever you're doing at. You know, it's a pretty rare occurrence that you have exactly the same material in your beam and your wire. Okay. If they're the same, then you can do that. But if they're different, then there you go.
Got it.
Yeah, I mean,
How would this be different if there's a gap?
so if there was a gap, let me show very quickly the setup for that. Okay, a gap, what would typically end up happening is you would have, say, W here, and then maybe, actually, let's just do it a roller support first. Okay, let's do a roller support located 0.2 meters away. All right, you're still going to evaluate your compatibility condition at x equals L. Okay, so problems with a gap. You're still going to have V total at x equals L. But now it's not just going to be equal to 0, right? Because we have a gap. So to factor in the gap, what I think is best to do is to use some test numbers. Okay. So in this case, let's consider if my left side was negative 0.2, that would imply that I'm just barely touching the roller support. Okay, so based off of that, I would say V total at x equals L is negative 0.2 meters. Okay. So pretty straightforward when it's just a roller, okay, or a rigid support. Okay, if it's a rigid support, you just locate what the actual deflection is. Here, because it's below the beam, it shows up as a negative.
But then if it touches the roller or goes past it, then isn't there some support reaction there?
There would be, right? But here for the roller support, first of all, it's not going to go past it because the roller is rigid. So the roller is not going to move. Okay. So you would have a support reaction. So your V total would still be, you would still have your primary beam is the distributed load. Okay. And your auxiliary beam is still BY. Okay. But when you put them together, it's not equal to 0. It's equal to negative 0.2 meters.
I see. So that's the only difference?
For when it's a rigid support. Now, if it's a flexible support and a gap, then it's even harder. Okay. So in that situation, you again still want to use test numbers. Okay. Let's say that we have something here with L, A, and E. Okay. And I'll again use the distributed load. Okay. So your tables are still going to give you this as your primary and auxiliary beam, and you're still going to evaluate it at x equals L. But the right side of your equation is even trickier. Not only do you have a gap, but then you also have to worry about the elongation of this flexible support, okay? So then as far as whether or not it shows up as positive or negative, right? Delta is going to be equal to by L2 over AE. Here, again, by is going to push your beam upwards. So by is going to show up as positive when you split it up like this. Therefore, this delta term is going to be positive, but if you have the beam going further in and causing by to get bigger and bigger, that means that your beam is moving further and further down. So it should be getting more and more negative, which means that your compatibility condition would have a negative on both terms. Okay? So you really need to think about things holistically when you're talking about flexible supports and with gaps together. Okay, so using test numbers is a good idea here. If we take that the beam deflects downwards by 0.3 meters, it's very straightforward to see how we would have, you know, negative 0.3 meters here. Okay, that means that this has to have a negative because it's the gap term. And then the delta, a shrinkage of 0.1 meters, also corresponds to the beam moving down. Okay, so that means that I have to have the negative here so that we're nice and consistent. Okay.
What do you think are the chances we get one of those kind of questions for the superposition?
Flexible, so well, I can guarantee you you're going to have some statically indeterminate problem on there. Okay, that's for sure because we have not tested that yet, and that's one of the outcomes of the class. As far as whether it's a case like this where it's just a rigid support, case like this where it's a flexible support, case like this where it's a gap, or a case like this where it's flexible support and the gap, I would say that it's pretty likely that it's either with a gap or with a flexible support. I have seen them ask a problem with a flexible support and a gap, but in recent years, it's much more common to do just one or the other. It's probably not going to be just a rigid support though, because that's very simple. All right, so I would say it'd be between, you know, one of these two cases here.
All right, sounds good. Thank you.
Okay. All right, well, we are 4 hours and 30 minutes in. So that is all the problems that I wanted to solve today. Are there any questions before we kind of wrap up here?
Can you quickly just remind us you said it at the beginning what the guaranteed questions would be for the free response? It was a torsion and
You'll have one problem that's axial, one problem that's torsion, one problem that's bending.
Great.
And axial doesn't just mean things where it's a pure axial load like this. Okay, it could be a problem where you have to do a little bit of geometric analysis. Like this right here, this would count as an axially loaded member problem.
Got it.
Okay. Scrolling to see if I didn't forget anything. Any other questions? All right, well, this is it, guys. So good luck with your studying. I will get this posted to Canvas. I see some names that have been here since literally the start, so I'm very impressed with you guys. Again, your questions really do make this review more helpful for everyone. So I really appreciate you guys sticking it out. I think there's a few office hours planned for tomorrow and I think early Wednesday. For the online group, good luck on your exam. And then for the in-person group, I will see you all on Wednesday. So I think with that, we'll go ahead and stop the recording.
You're going to post this right now?
Not right now because it needs to download first. And this is a 4.5 hour video. That'll take a minute, but I will get it posted as soon as I can.
Thank you so much, Alan. Really appreciate your time.
All right, no problem.
Thank you.
Yeah, thank you.
Thank you so much, Alan.
My pleasure.